Imagine a planet that has experienced billions of years of changes, alternating between cycles of heat and cold, witnessing grand catastrophes and the slow but inevitable transformation of landscapes. Earth is not just the place where we live, it is an archive of colossal events, from powerful volcanic eruptions to subtle changes in vegetation. Over these billions of years, processes have shaped its surface, created mountain ranges, and eroded valleys. These changes occurred over a time span that is hard for us to comprehend, and in each of these epochs, there were forms of life that came and went, leaving their traces in the form of fossils and imprints on the surface. And then, amidst this grand panorama, humanity appears, a tiny spark in time, emerging against the backdrop of millennia-long processes. When we look at the remnants of ancient civilizations, we perceive them as evidence of the diversity of lives and cultures that, like us, sought their place in this boundless world. Our ability to create and destroy, build and destroy, and interact with one another and our environment makes us unique beings, yet it also reminds us of how fragile and ephemeral our lives are in this vast, eternal continuum. In this context, it is important to understand that every detail, from a simple stone to the complex architecture of ancient temples, is not just an artifact, but a part of history that leads us back to the origins of life on Earth. Around us are billions of years that form a mosaic of events, and each new layer reveals secrets that we barely knew existed. For example, when you look at ancient ruins, do you know that beneath them there might be even older structures built long before our ancestors began to inhabit this world? Archaeologists often find traces of long-lost cultures that inscribed their knowledge in stone and clay, leaving us riddles and questions to which we are just beginning to find answers. The age of Earth is 450 million years, and during this time it has passed through numerous stages of its existence. At the beginning, when the planet was just forming, its surface was scorching and hostile. The atmosphere, primarily composed of water vapor, carbon dioxide, and ammonia, gradually changed, allowing sunlight to reach the surface. The time that has passed since then creates a vast interval for the possible development of intelligence. Ancient science. This long and complex path to the intelligence we possess today is the result of an infinite number of events. Deep time is a concept that helps us grasp the immense scales of Earth's history. Imagine that the entire history of our planet, which spans about 4.5 billion years, fits into the framework of just one day. In this geological time frame, if we consider that one day consists of 36,580 seconds, each moment would represent millions of years. Therefore, life on Earth emerged around 3.5 billion years ago, which corresponds to roughly 3 in the morning. 800 million years ago, when the evolution of multicellular organisms began, it was around 8 in the morning. The appearance of dinosaurs occurred around 230 million years ago, which is around 3 in the afternoon. Their extinction was recorded approximately 65 million years ago, corresponding to just 2 minutes before midnight. Human ancestors began to form around 7 million years ago, which is only a few seconds before midnight. Finally, the emergence of modern humans, Homo sapiens, happened around 200,000 years ago, which in our metaphor is just 1 second before midnight. This concept not only illustrates the brevity of human history in the context of geological time, but also highlights the scale and significance of the processes that occurred on our planet long before humans appeared, such as the formation of continents, climate change, and the development of ecosystems. The Fermi paradox is a philosophical question that addresses the striking contradiction. If the universe is filled with countless stars and potentially habitable planets, why do we not observe any signs of intelligent life that might inhabit them? This question gives rise to numerous hypotheses and theories. Some researchers suggest that intelligent civilizations may exist, but are too far away for us to detect. Others believe that such civilizations might be technologically advanced and deliberately avoiding contact with us. There is also the idea that life on other planets might evolve along entirely different paths, making it unrecognizable to us. Some scientists argue that intelligent life might be extremely rare, and that we are among the few that have reached a certain level of development. The Fermi paradox also prompts us to consider our own path of development and whether we will ever become part of this cosmic picture if and when we find other intelligent beings. Reflecting on this, many questions arise about the conditions necessary for the emergence of life and intelligence, as well as what we can do to advance our own understanding of the universe. It is important to note that even if we do not see clear evidence of other civilizations, this does not mean they do not exist. The Silurian Hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, challenges traditional views on the development of civilizations on Earth. They question whether a technologically advanced civilization could have existed on our planet long before the appearance of humans. To address this question, researchers study the geological history of Earth and attempt to determine if there is evidence of such civilizations in the past. They focus on various climatic changes that occurred on the planet, and how these changes might have influenced the potential progress of intelligent beings. For instance, about 400 million years ago during the Silurian period, Earth's conditions were significantly different. The atmosphere was rich in oxygen, and the oceans teemed with life. This created ideal conditions for the development of complex life forms. Schmidt and Frank investigate how, with the necessary resources and conditions, intelligent life could have emerged and created technologies. They also emphasize that mass extinctions, such as the one that occurred 65 million years ago, could have erased all traces of such civilizations. Research indicates that even if they existed, their achievements could have been destroyed by natural disasters. Additionally, researchers analyze whether other planets in our solar system, such as Mars, could contain evidence of possible ancient civilizations, adding further intriguing aspects to this hypothesis. The Silurian hypothesis opens new horizons for understanding not only our past, but also the possibilities of life in other forms and on other planets. This concept raises many questions about how we perceive the development of intelligent life and its place in Earth's history. Over time, various factors such as erosion, tectonic movements, and other natural phenomena can completely erase all evidence of these cultures' existence. This presents challenges for archaeologists in finding and interpreting historical artifacts. This creates unique challenges for researchers trying to reconstruct the picture of ancient life and understand how people interacted with their environment. It is important to note that geology and history are two sides of the same coin, as changes in the Earth's crust directly influence how we perceive and study the past. For instance, the constant influence of water and wind causes ancient Greek marble temples to lose their original shape, with details that were once clearly visible becoming blurred and indistinct. Meanwhile, wind, which blows sand and small particles, acts as an abrasive tool, washing away rocks and accelerating the destruction process. Erosion does not spare metallic structures either. Under the influence of moisture and oxygen, metal oxidizes, forming rust, which over time weakens even the strongest frameworks. Thus, famous statues, such as the Christ the Redeemer statue in Rio de Janeiro, are subjected to the influence of marine air, leading to the formation of corrosion and the need for periodic restoration. This destructive process is not limited to architecture. It also affects the landscape, altering river courses and creating new relief forms such as canyons and gorges. For example, the Grand Canyon in the United States was formed over thousands of years due to the slow but steady erosion of water, which gradually deepened its course, destroying rocks. Erosion is not just destruction, it is a continuous process that transforms the surrounding world, and in this context, it becomes an integral part of the geological history of the planet. Tectonic movements of the Earth's crust are the foundation upon which the face of our planet is built. Continental plates do not remain stationary. They collide, diverge, and subduct beneath one another, creating mountain ranges and oceanic trenches. For instance, when two plates collide, one may subduct beneath the other, a process known as subduction. This not only shapes the landscape, but also leads to the formation of volcanoes and earthquakes. Against this backdrop, all traces of civilizations that once existed on the surface gradually disappear, swallowed by the Earth's mantle. Recall the ancient city of Pompeii. Its destruction was due to the eruption of Vesuvius, but it was tectonic processes that formed the mountain itself. Such events occur worldwide, from the Himalayas, which are rising before our eyes, to the Mariana Trench, which consumes everything that falls into its depths. It is impossible not to mention that on the borders of plates, where the most active tectonics occur, archaeologists find remnants of cultures that may ultimately be swallowed or destroyed. For example, in subduction zones, archaeologists find artifacts that were there only a few thousand years ago but could disappear due to plate movements. Thus, tectonic processes not only alter the landscape but also impact the preservation of historical heritage, carrying away any evidence of human existence, leaving only mysteries hidden within the Earth's depths. Accumulation of sediments. This is a process where rocks and organic materials accumulate on the surface of the Earth, forming layers that gradually bury all traces of human activity and natural objects. Initially, particles like sand, silt, and clay settle at the bottom of rivers, seas, and lakes, forming sedimentary rocks. Over time, these layers begin to accumulate, and their weight presses down on the underlying layers, causing them to compress. This process can take millions of years, during which various materials, including animal remains and plant debris, accumulate and eventually turn into fossils. At depths where the pressure becomes sufficient, chemical reactions occur that cause the particles to cement together and form a monolithic rock. For example, limestone is formed from calcite, which is created from microscopic marine organisms, and sandstone is formed from grains of sand that are bound together. These layers not only preserve the remains of ancient ecosystems, but also serve as repositories for artifacts left by humans. They can tell stories about how cultures developed, what technologies were used, and how people adapted to changing environmental conditions. Sediment accumulation is not just a physical process. It is the key to understanding the past, helping archaeologists and geologists reconstruct the picture of what the Earth looked like millions of years ago. In places like the Grand Canyon in the United States, one can observe numerous layers, each telling its own story about geological epochs and climate changes. These windows emerge due to the combination of various factors: climatic changes, availability of resources, social structures, and interactions between cultures. For instance, it is important to note that these windows are not universal. Their existence and duration depend on the specific conditions of the region. In different parts of the world, the same temporal window can manifest differently. Some peoples may build monumental structures, while others focus on trade and the exchange of knowledge. It is also important to consider that temporal windows can overlap when several civilizations develop simultaneously, creating complex interactions that influence their fates. Archaeologists studying such interactions find traces of trade, cultural exchange, and even conflicts, adding depth to the understanding of the dynamics of these periods. Ultimately, temporal windows serve as a key to understanding not only the successes, but also the failures of human societies, allowing us to trace how they responded to the challenges of their time. For example, the study of temporal windows shows that in some regions, such as the Nile Valley, agriculture became the basis for sustainable development, while in others, such as regions with limited resources like the Sahara, completely different. Survival strategies emerged. During the diversity of flora and fauna began to increase. On land, the first terrestrial plants appeared, while in the oceans, fish and mollusks thrived, creating a rich ecosystem. At this time, there were also substantial reserves of resources such as carbon compounds, which could be used for the metabolism of living organisms. The Silurian period is notable for the emergence of the first vertebrates, which could evolve more complex social structures. Research indicates that it was during this period that numerous adaptations occurred, which could later lead to the emergence of more complex life forms. At this time, the first terrestrial ecosystems also began to form, opening the way for further diversification of life on Earth. The Carboniferous period, which spanned from 359 to 299 million years ago, was an era when Earth's atmosphere became rich in oxygen, creating ideal conditions for the evolution of complex life forms. The forests of that time were dominated by giant ferns, conifers, and other plants that could reach heights of up to 30 meters. These forests not only converted carbon dioxide into oxygen, but also provided habitats for a multitude of organisms. During the Carboniferous period, insects, including giant dragonflies with wingspans exceeding 50 centimeters, began to flourish. Additionally, the first amphibians appeared, starting to colonize land, including ancient forms like Leposaurus. At this time, vast swamps formed, facilitating the accumulation of organic material that later became the foundation for coal deposits. The flora and fauna intertwined to form complex ecosystems, with biodiversity reaching its peak, laying the groundwork for future ecological systems. Carbon, which accumulated through the decomposition of vegetation, influenced the climate, creating warm and humid conditions that fostered further life flourishing. As a result of these processes, Earth began to form massive coal deposits, which are still utilized by humanity as a source of energy. The Permian period, which lasted from 299 to 252 million years ago, was a time of flourishing terrestrial ecosystems on Earth. During this period, vast forests emerged on the continents, primarily composed of ancient ferns and conifers, such as primitive pine trees. Giant plants resembling modern cycads also developed, reaching heights of up to 30 meters. The flora of the Permian period was diverse and included many forms of life adapted to various climatic conditions. This time also saw the appearance of the first reptiles, ancestors of dinosaurs, which contributed to the further development of the animal world. Under such conditions, a highly developed civilization capable of creating complex social structures and technologies could have theoretically emerged. At this time, large predators like dinocephalians, which could reach lengths of up to 4 meters, and herbivores like anoplotheres, which fed on vegetation, existed. These animals already possessed some characteristics that could later contribute to social organization and cooperative hunting. However, fauna. Despite all the achievements and diversity of life, the Permian period ended in a catastrophe that left the planet almost devoid of life. Scientists continue to study the causes of this mass extinction, proposing hypotheses about volcanic activity, climate change, and other factors that could have played a crucial role in this event. Mass extinctions are large-scale events that fundamentally altered Earth's biosphere and led to the disappearance of a significant number of species. These catastrophes affected not only specific groups of organisms, but entire ecosystems, leaving behind voids that required millions of years to recover. They occurred at various levels, from local to global, and despite differences in causes, they shared one common trait. They erased the traces of the past, altering the course of evolution on the planet. Throughout Earth's history, there have been several mass extinctions, each of which was a turning point in the development of nature. This created conditions for the emergence of new forms of life and fundamentally altered biological diversity. Scientific research shows that the consequences of mass extinctions were so profound that they determined the evolutionary paths for future generations of animals and plants. In the context of these events, it is important to note that each catastrophe left behind unique conditions that fostered the emergence of new ecosystems. Studying these processes helps scientists understand how life on Earth adapted and evolved in the face of sudden environmental changes. For example, after one of the mass extinctions, dinosaurs appeared on Earth and dominated the planet for millions of years. Considering the scale of these events, it becomes clear that they not only destroyed, but also created new opportunities for life. As a result of these changes, the species that survived often adapted and evolved, filling the ecological niches that became available after the disappearance of their predecessors. This underscores the importance of understanding the mechanisms behind mass extinctions and their impact on the evolution of the biosphere as a whole. Research shows that in each epoch, changes in climate, volcanic activity, and other geological processes could serve as catalysts for these catastrophes. For example, recent findings confirm that the location and timing of these events were crucial in shaping new ecosystems. The Permian extinction occurred approximately 252 million years ago and is considered the most catastrophic event in Earth's history, with around 96% of marine and 70% of terrestrial species disappearing. This event dramatically reset the course of life on the planet. Over the course of several million years, ecosystems underwent significant changes. Against the backdrop of global warming due to volcanic activity, there was widespread oceanic anoxia, which destroyed oxygen zones and led to the demise of many marine organisms. Volcanoes in Siberia released vast amounts of carbon dioxide and other greenhouse gases, contributing to a sharp rise in temperature. Additionally, changes in sea level also played a role, as fluctuations in water levels affected coastal ecosystems where many species lived. The evolutionary changes that followed this extinction paved the way for the emergence of dinosaurs and other modern groups of organisms. Notably, it was after the Permian extinction that the transition to the Mesozoic era occurred, which saw the rise of reptiles and the appearance of the first mammals. Multiple factors, including climate change, volcanic eruptions, and changes in atmospheric composition, contributed to this global crisis, which altered the course of evolution. In scientific circles, the specific causes and mechanisms of this mass extinction are still debated, highlighting its complexity and the multitude of factors that led to such a catastrophic outcome. The Cretaceous-Paleogene extinction event occurred 66 million years ago and is one of the most famous mass extinctions in Earth's history. Approximately 75% of all species on Earth perished as a result of this catastrophe. Research indicates that the asteroid impact caused significant changes in ecosystems, triggering a chain reaction of species extinction. These conditions would have made survival practically impossible for complex forms of life that require a stable ecosystem. Research shows that even outside the impact zone, in conditions of insufficient light and rapid climate change, the survival of large mammals and other species would have been extremely difficult. As a result of this event, a new era began on the planet, during which mammals were able to occupy the ecological niches left vacant by the extinct dinosaurs. Geological markers are specific features in stratified rocks that can reveal past events and conditions on Earth. They represent traces left by nature or by the activities of living organisms and can serve as indicators of changes in ecosystems. By studying these markers, scientists can identify significant changes that occurred on the planet, such as climate changes or the appearance of new species. It is worth noting that these markers can also indicate the presence of a technological civilization. For example, they can show signs of mass production, changes in soil composition, or even traces of urban structures left behind by civilizations. When analyzing these geological markers, researchers can understand how species adapted to new conditions and what technologies were used to cope with environmental challenges. These markers serve as temporal markers that help reconstruct the picture of life's evolution on Earth. The question of which specific changes can be recorded in geological layers remains a topic of debate among scientists. Scientists also draw attention to unusual concentrations of rare metals in geological layers, which may indicate the extraction and processing of resources by intelligent beings in ancient times. For instance, in some places, high levels of gold, copper, and platinum have been found, suggesting that our ancestors used primitive technologies to extract these metals. Specifically, in South America, in the Andes region, copper deposits were discovered that could not have formed naturally and are likely linked to the activities of ancient civilizations such as the Incas. In other regions, such as Africa, geologists found anomalous concentrations of cobalt and nickel, which may also be connected to the processing by local tribes. These findings challenge traditional views on how technologies developed in the past. Some researchers even suggest that such concentrations could be the result of ancient metallurgical methods that have been lost over time. It is important to note that there is no consensus on how exactly these metals were processed and what specific technologies were used. This opens up new avenues for research and discussion, as the discovery of rare metals can change our understanding of ancient civilizations and their level of development. For example, in some samples from Mesopotamia, traces of mercury were found, indicating the possibility of complex metallurgical processes that were previously considered impossible for that time. Scientists continue to analyze these samples to determine which technologies were used and how they could have influenced cultural development. Facts: anomalies in the isotopic composition of ancient rocks have piqued the interest of scientists, as they may indicate the presence of artificial nuclear reactions or other technological processes that occurred millions of years ago. For instance, in some samples of rocks from South Africa, unusual ratios of carbon and oxygen isotopes have been found, which do not correspond to natural processes. These findings challenge the traditional understanding of the technological progress of ancient societies. Further, in particular, in rocks found in the Indian Ocean region, researchers have found traces of isotopes that are only formed in nature as a result of high-energy reactions. These anomalies raise numerous questions about what technologies might have been available to our ancestors and what processes occurred on Earth in those distant times. For example, in some samples taken from layers over 1 million years old, traces of isotopes have been found that could not have formed without human or other intelligent beings' involvement. Such discoveries underscore that the study of ancient rocks can reveal new horizons in our understanding of the history of our planet and possible civilizations that existed long before us. Modern research into ice and sedimentary layers indicates that in certain regions, traces of pollutants have been found, which could suggest the existence of civilizations with advanced industrial technologies. For instance, these findings suggest that even in prehistoric times, societies capable of environmentally destructive actions may have existed. Scientists speculate that such traces could be the result of civilizations that may have used coal or other resources, although the technologies we understand today might not have existed during their time. It is important to note that these data are not yet definitively interpreted, as many of them require further study and verification. Nevertheless, the results of the analyses have already raised questions about how long ago humanity began to impact nature and what consequences this could have had for the environment. These changes could have been the result of agricultural practices or early forms of industrialization, challenging our understanding of how ancient societies developed and interacted with each other. Archaeological search methods have their limitations, especially when dealing with civilizations that existed tens or hundreds of millions of years ago. Secondly, factors such as erosion, tectonic movements, and climate changes can completely erase the traces of ancient civilizations. For periods far removed from our own, many material evidence could have been destroyed or inaccessible for discovery. Additionally, the complexity also lies in the fact that even if we found certain artifacts, their interpretation would require an extremely cautious approach, as the context of their discovery could be entirely different from that of later civilizations. Such a situation necessitates a reevaluation of research methods and approaches to data analysis, making archaeological research in this context particularly challenging. Many of these factors have no parallels in later history, leading to the need to develop new theories and hypotheses. Fossilization is a rare phenomenon that results in only a minuscule fraction of all organisms that have ever existed on Earth being preserved. For fossilization to occur, specific conditions are necessary. The organism must quickly be buried to avoid decomposition and exposure to destructive factors such as bacteria and oxygen. Most organisms decompose, and their soft tissues leave no trace in fossilized form. Even in ideal conditions, fossilization only occurs if the organism enters a mineral-rich environment, such as sedimentary rocks. Therefore, when considering the entire biosphere that has existed over billions of years, only 1 out of every 100,000 organisms becomes fossilized. This makes the discovery of fossilized remains of intelligent beings highly unlikely. For instance, Homo sapiens has only existed for about 200,000 years, and only a small number of individuals have preserved their remains. Furthermore, even if organisms are preserved, their fossilization may occur under conditions that are not suitable for the creation of detailed remains, such as fossils with well-preserved skulls or teeth. Additionally, geological processes like erosion and plate tectonics can destroy potential finds. Scientific research indicates that out of all known fossils, only about 30% can be attributed to mammals, and among them, only a limited number can be traced back to human ancestors. The process of metamorphism of rock formations is a complex transformation that occurs under the influence of high temperatures and pressures within the Earth's crust. In this process, initial minerals become unstable and begin to alter their crystalline structure. Temperatures required for metamorphism can reach several hundred degrees Celsius, while pressures can reach hundreds or even thousands of atmospheres. These conditions create an environment in which mineral molecules rearrange, forming new minerals such as mica, quartz, or garnet. As a result of this process, the original structure of rock formations is completely altered, and any traces of previous processing or use by intelligent beings disappear. For example, limestone subjected to metamorphism transforms into marble, completely losing its original characteristics and texture. Metamorphism can occur due to contact with hot magma flows or prolonged pressure at great depths. This process can also result in the formation of various textures, such as banding or layering, which indicate multiple changes in conditions. Metamorphism plays a crucial role in the cycle of the lithosphere, and its effects can be observed not only in geology but also in archaeology, where it complicates the determination of age layers that could contain artifacts. Subduction is one of the most significant geological processes, involving the sinking of oceanic crust beneath continental crust. This process occurs at the boundaries of tectonic plates, where denser oceanic crust collides with lighter continental crust. As a result of this collision, the oceanic plate begins to descend into the Earth's mantle, creating deep oceanic trenches, such as the Mariana Trench. As the oceanic crust descends into the mantle, it melts, and with it, any evidence of civilizations that once existed on submerged continents is lost. This makes it challenging for archaeologists to find artifacts that could indicate ancient cultures that once inhabited these areas. For instance, many ancient oceanic islands, such as Lemuria or Atlantis, are believed to have sunk due to subduction processes, and their possible existence continues to be a topic of debate among scientists. Information about such civilizations can be carried to depths where temperatures and pressures are so high that any organic materials are destroyed. This process can also lead to the formation of volcanoes, as molten rock rises to the surface, creating new land formations but also erasing traces of those who lived on these lands. Subduction, therefore, not only shapes the landscape but also erases the historical memory of civilizations that could have left their mark on these submerged continents. Consequently, archaeological research in areas where subduction has occurred often yields disappointing results, as any trace of ancient cultures is irrevocably lost. Alternative forms of reason challenge traditional notions that intelligence and consciousness are exclusively human or primate characteristics. This idea posits the existence of various cognitive systems that can manifest in diverse forms, distinct from those observed in humans or their closest relatives. For instance, these forms of reason may include unique ways of perceiving the world, processing information, and interacting with the environment, which need not conform to human standards. In this context, reason can manifest through complex systems of communication, adaptation to the environment, and problem-solving that may be entirely different from those used in human society. These forms of reason may have their own mechanisms of learning, memory, and even emotional responses, creating unique ways of interacting with the world. Research indicates that such alternative forms of reason can be just as complex as human reason and capable of innovation and adaptation in response to changes in the environment. Therefore, studying these forms of reason can shed light on the nature of intelligence in general and broaden our understanding of various ways of existence and interaction with the world. Recent advancements in neurobiology and cognitive science are opening new horizons in understanding these alternative forms of reason, revealing their diversity and complexity. It is important to note that these systems may not adhere to the same laws as human consciousness and may employ entirely different approaches to solving tasks that we consider familiar. This underscores that reason can take many forms, and it is not appropriate to limit its understanding to human characteristics alone. The study of such alternative forms of reason may lead to new discoveries and approaches in the sciences of life and consciousness. New methods of observation and analysis offer the possibility of better understanding how various beings perceive and process information, which can have significant implications for science and philosophy. The development of intelligence in reptiles, particularly dinosaurs, is an intriguing area of study, especially when considering the group of troodontids. These dinosaurs, which lived around 100 million years ago, were notable for their relatively large brains, which made up about 12% of their body mass. This is a significant proportion for reptiles of that time. Troodontids had a well-developed sensory system, allowing them to not only hunt effectively, but also adapt to changes in their environment. Their keen vision and complex teeth indicated a varied diet, which could have contributed to the development of cognitive abilities. Unlike many other reptiles, troodontids likely had higher levels of social organization, suggesting a certain level of intelligence. Remarkably, some fossil finds have revealed signs of nesting, which could indicate parental care. These factors, combined with their adaptability, allowed troodontids to thrive in various ecosystems, contributing to the overall evolutionary success of reptiles. For a long time, they dominated the Earth, demonstrating their ability to survive and adapt. Currently, there is ongoing debate in paleontology about the extent of their intellectual capabilities, and research continues with each new discovery. Some scientists suggest that the brain structure of troodontids may have been more complex than that of most of their contemporaries, opening new avenues for understanding the evolution of intelligence in reptiles. Fossil remains indicate that troodontids may have had unique adaptations that facilitated more complex behavior. The potential for the development of intelligence in cephalopods, particularly octopuses, is a subject of great interest among scientists. Octopuses possess one of the most complex nervous systems among invertebrates. Their brain contains approximately 500 million neurons, comparable to the brain of a dog. These mollusks are capable of learning and exhibit remarkable problem-solving skills. For instance, in laboratory conditions, octopuses successfully open cans to obtain food. This indicates that they can not only perceive information, but also process it, making conscious decisions. Additionally, octopuses use tools, which is a rare phenomenon among animals. They can employ coconut shells or empty mollusk shells as shelter or for protection. Research shows that octopuses are capable of mimicry. They can imitate the behavior of other octopuses or even fish, which suggests a developed social interaction and understanding of their environment. Emotional reactions in octopuses, such as changes in skin color based on their mood, also point to high cognitive functions. In some cases, they even exhibit signs of individuality, differing in behavior and preferences. This raises questions about how complex the consciousness of these creatures might be, and how it compares to the intelligence of other animals. Research continues, and questions about how exactly octopuses perceive the world remain open. Scientific experiments confirm that octopuses can adapt to new conditions, demonstrating exceptional learning and memory abilities. In one experiment, octopuses were able to remember the location of objects and find them after several days. Arthropods, particularly social insects, possess a unique evolutionary potential that makes them prime candidates for the creation of collective intelligence and complex architectural structures. For instance, ants build colonies that can reach tens of millions of individuals, organizing their efforts to create intricate systems of tunnels and chambers. In such colonies, there is a clear division of labor. Worker ants are responsible for foraging, construction, and defense, while the queen focuses on reproduction. Bees, on the other hand, construct hives with remarkable architectural precision, using wax cells that not only store honey, but also provide optimal conditions for the development of larvae. These social insects also exhibit complex forms of communication, such as the dance of bees, which conveys information about the location of food sources. Wasps and termites, also social insects, build nests that can reach several meters in height, and are true engineering marvels. Termites, for example, create sophisticated ventilation systems that regulate temperature and humidity within their nests, allowing them to survive in the most adverse conditions. These examples highlight that social insects not only possess exceptional abilities for cooperation, but can also create structures that are the result of collective intelligence, suggesting that they may develop forms of intelligence distinct from human intelligence. The collective behavior of ants, bees, and termites already today attracts the interest of scientists studying the possibilities of artificial intelligence and robotics, as the principles underlying their interactions can be applied to the creation of autonomous systems. Research shows that in some ant colonies, decisions are made not at the level of individual ants, but at the level of the entire community, opening new horizons for understanding collective intelligence as a phenomenon. The concept of convergent evolution is an intriguing phenomenon where different organisms lacking close genetic relationships develop similar traits and adaptations in response to similar ecological conditions or challenges. This process can be compared to how different architects can create similar buildings using the same materials and techniques, yet having no relation to each other. Convergent evolution demonstrates how nature, facing similar problems, finds optimal solutions regardless of genetic factors. For instance, in the same climate, similar body forms, sizes, and even behavioral patterns can emerge, significantly increasing the chances of survival in highly competitive or changing environments. This phenomenon underscores that adaptation is not always linked to heredity and kinship, but rather to the necessity of survival. This approach allows for the study not only of biological, but also of ecological relationships, showing how different species can respond to the same ecological niches. Convergent evolution thus opens new horizons for the study of evolutionary processes, illustrating how the diversity of life on Earth can be a result of similar adaptations to common conditions. In this context, it is worth noting that understanding these processes can aid in the study of both living and extinct species, as well as in predicting possible paths of adaptation in the future. Convergent evolution of the eye invertebrates and cephalopod mollusks provides a striking example of how complex organs can develop independently in different evolutionary lineages. In vertebrates, such as fish, birds, and mammals, eyes have a similar structure: cornea, lens, retina, and pupil, allowing them to effectively perceive light and form images. Meanwhile, cephalopod mollusks, such as octopuses and squids, have evolved eyes that are functionally similar to those of vertebrates, but have a completely different anatomical structure. For instance, squids lack a vitreous body, and their pupil is shaped like the letter W, whereas in vertebrates, the pupil is circular. These structural differences result in optical systems that operate on different principles, but the ultimate goal of perceiving the environment remains the same. Research shows that despite different evolutionary paths, both types of eyes provide a high level of visual information, demonstrating how similar ecological conditions can lead to similar adaptations in different groups of organisms. For example, both types of eyes have photoreceptors for light perception and mechanisms to regulate the amount of light reaching the retina. Nevertheless, mollusks and vertebrates have different proteomic patterns, indicating unique molecular pathways leading to the formation of these complex organs. The study of convergent evolution of the eye not only highlights the adaptive capabilities of living beings, but also opens new horizons in understanding biological processes occurring on our planet. Scientists continue to investigate these systems to understand how they developed and what factors influenced their formation. In this context, it is important to note that despite the differences, both groups of animals have achieved a high level of visual adaptation. Convergent evolution of echolocation in bats and cetaceans is a striking example of how similar ecological pressures can lead to the development of analogous adaptations in different groups of animals. Bats, which began using echolocation around 60 million years ago, emit high-frequency sounds and then detect the echo returning from objects, allowing them to navigate in darkness and find prey. Their auditory system is adapted to perceive these sounds, ensuring high precision in determining the distance and size of objects. On the other hand, cetaceans like dolphins and whales have developed a similar ability in an aquatic environment, where sound waves propagate differently. They also use sound signals that can travel long distances underwater and, like bats, analyze the returning waves to gain information about their surroundings. Notably, despite evolutionary divergence, both groups of animals have arrived at similar solutions: the presence of specialized organs, such as nasal passages in whales and specific structures in bats, that direct sound. This confirms that complex sensory systems can arise independently in response to similar environmental challenges. For instance, research shows that dolphins can recognize objects by their size and material, similar to how bats determine their prey. Convergent evolution of intelligence is observed not only in dolphins and bats, but also among primates and corvids. Primates such as chimpanzees and orangutans have developed high cognitive abilities that allow them to solve complex problems, use tools, and even exhibit social interaction skills that resemble those of humans. For instance, chimpanzees can use sticks to extract termites, demonstrating planning and understanding of cause and effect relationships. Meanwhile, corvids like crows and jays also exhibit high intellectual activity. They can solve tasks that require multiple steps to achieve a goal, such as using objects as tools to obtain food. Research shows that some corvid species can even create and use their own tools, placing them on par with primates. These examples indicate that high cognitive abilities could have evolved in different animal groups across various geological epochs under the influence of similar ecological factors. It is interesting that in different ecosystems, such as tropical forests or mountainous regions, primates and corvids have used their intellectual abilities to adapt to their surroundings. As a result, despite evolving independently, these groups of animals display remarkable similarity in their intelligence. This phenomenon underscores that complex cognitive processes can arise in response to similar challenges, regardless of the phylogenetic relationships between species. Notably, corvids like the New Zealand kiwi stand out with their unusual behavioral traits, which also suggest a high level of intelligence. The concept of technological singularity refers to a moment when technological progress reaches such a speed that it becomes unpredictable and transcends human comprehension. This state is characterized by a sudden acceleration of processes, causing familiar notions of time, space, and even life to change. Imagine changes happening so rapidly that humanity cannot adapt to new conditions, and traditional socio-cultural norms begin to lose their relevance. A key aspect of singularity is that development is not linear. It accumulates exponentially. Instead of gradual steps, we observe situations where achievements in one field of science or technology trigger immediate changes in others, creating a domino effect. This leads to the exacerbation of social, economic, and even ethical issues, forcing societies to reevaluate their views on progress and its consequences. When we speak of such acceleration, we must consider that it affects all aspects of life, including education, work, and even personal relationships. In such a dynamic environment, traditional approaches to learning and development begin to seem outdated, and humanity faces the need to rethink its role in a world where everything is changing rapidly. This creates an atmosphere of uncertainty and anxiety, but also opens new horizons for creativity and innovative thinking. The challenge lies in the fact that in conditions of singularity, there is no clear plan of action, and many questions remain open. For example, how do we adapt to new conditions? How do we maintain humanity in a world of high technology? These and many other questions require deep analysis and rethinking, as the consequences of technological singularity can affect not only individual nations, but the entire planet. It is interesting to note that during this transformation, there arises a need for a new understanding of the interaction between people and machines, as well as the creation of new ethical norms that correspond to this rapidly changing world. Exponential growth of technology and human civilization over millennia is striking in its dynamism. The first stone tools created over 2 million years ago laid the foundation for further progress. These simple stone tools allowed our ancestors to hunt and process food, which in turn led to the development of social structures and the exchange of knowledge. With the transition to an agricultural society around 10,000 years ago, mass food production began, contributing to population growth and the emergence of the first cities. The Renaissance in the 14th to 17th centuries was an era of remarkable inventions, such as Johannes Gutenberg's printing press, which revolutionized information dissemination. This evolution of technology in human history demonstrates how quickly civilizations develop and raises the question of whether similar processes could have occurred with other intelligent species in the cosmos. For instance, it is possible that on other planets, intelligent beings also began with simple tools, gradually mastering complex sciences and technologies, ultimately leading to space travel. In this context, it is worth considering how different conditions on other planets might influence the pace and direction of technological progress. The concept of the technological horizon posits that there exists a certain limit beyond which a civilization may become invisible or inaccessible to external observation. This can occur for several reasons. Secondly, civilizations may transform, transitioning into a new state of existence, possibly through uploading consciousness into virtual worlds or creating artificial intelligence that manages all aspects of life, leaving the physical world outside their interests. Such development can lead to the disappearance of visible signs of their existence, as they may choose to live in the digital realm, where they do not interact with the surrounding environment in the way we are accustomed to. This phenomenon also raises the question of how other civilizations might perceive the disappearance of a more advanced culture, as the absence of signals could be interpreted as a sign of extinction or as a result of evolutionary changes. Civilization may follow its own unique trajectory, and understanding this process requires a deep analysis of technological, social, and cultural factors that may influence their development. This concept implies that not all cultural artifacts or technological achievements are equally preserved or discovered during archaeological excavations. Additionally, technologies used in different periods can change their visibility depending on their level of spread and use in society. For instance, if certain technologies were widely used, they may leave more traces than those used only in limited regions or among a narrow circle of people. Archaeological visibility also depends on research methods. Different techniques may reveal some objects better than others, leading to an uneven representation of cultural heritage. This in turn creates challenges in interpreting data and forming a complete picture of historical development. Researchers must consider these factors to avoid distortions in understanding the past, as undiscovered materials can tell equally important stories. For example, technologies that did not leave obvious traces may indicate unique aspects of life and culture that would otherwise remain unnoticed. It is important to understand that archaeological visibility is not a fixed quantity, but constantly changes based on new findings and analysis methods, significantly influencing our understanding of the past. Stone is one of the most durable building materials, capable of enduring for millions of years, but its longevity depends on geological conditions. For instance, granite and basalt, being highly resistant and resistant to erosion, can remain virtually unchanged for millions of years if not exposed to aggressive environments. Conversely, limestone, widely used in ancient construction, is more susceptible to destruction, as it dissolves in acidic rain, leading to its degradation. This explains why even magnificent stone structures of ancient civilizations, such as the temples of the Maya or the pyramids of ancient Egypt, can disappear from the face of the earth. Over time, water and climate changes, many of these structures have been subjected to corrosion and destruction, leaving behind only ruins or even complete disappearance. For example, in Mesopotamia, where some of the earliest stone buildings were constructed, many of them did not survive to our time, as climatic conditions and the lack of adequate protection from natural factors contributed to their destruction. It is also important to consider that even if stone blocks are preserved, they can be moved to other locations or used in new constructions, which also reduces the number of surviving original structures. In the end, even the most robust stone buildings can fall victim to time and the surrounding environment, emphasizing the fragility of human heritage in the context of geological processes. Metals, even the strongest and most durable alloys, are susceptible to corrosion and oxidation, making them short-lived on geological timescales. For instance, iron begins to rust within a few years if not protected from moisture and oxygen. As a result, structures that once appeared impressive can crumble into dust within a few decades. Bronze artifacts created more than 3,000 years ago have sometimes survived due to unique burial conditions, but even they are subject to destruction by the surrounding environment. Steel, despite its strength, loses its properties when exposed to moisture and various chemical substances that accelerate oxidation. Over tens of thousands of years, even the highest quality metallic objects become unrecognizable under the onslaught of time. For example, during excavations of ancient Greek and Roman cities, archaeologists find remnants of metallic tools that have survived only as oxides and rust. These processes demonstrate that the metal we consider eternal can be surprisingly fragile in the long term. In contrast to stone, which can withstand millions of years, metal requires constant care and protection, otherwise it quickly deteriorates. Various factors such as temperature, humidity, and the chemical composition of the surrounding environment play a critical role in the speed of corrosion. For example, in marine conditions, metallic structures deteriorate significantly faster due to salt water, which accelerates corrosion processes. Thus, over the course of millennia, even the most reliable metallic artifacts disappear due to natural processes of destruction. The situation with organic materials is even more tragic. Wood, fabrics, paper, and other biological materials decompose within a few years or centuries, leaving behind mere ghosts that cannot be restored. For instance, wooden structures like ancient ships can survive in the conditions of marshes or peat bogs, but in ordinary conditions, they quickly rot due to the influence of moisture and microorganisms. Artifacts made of fabric, such as the clothing of ancient peoples, can disappear within a few decades if not properly protected. Even parchments and manuscripts, which once held knowledge and history, are subject to destruction due to changes in temperature and humidity, leading to their decomposition. In some cases, researchers find only charred remnants that speak of long-gone civilizations, but do not allow us to understand the details of their daily lives. For example, in Mesopotamia, archaeologists discovered charred textile items that were once part of everyday life, but now can only tell us about the time of their demise. In other cases, such as the finds in the tombs of pharaohs, Organic materials have survived only due to unique burial conditions, such as a dry climate and the hermeticity of the chambers. However, even in these cases, some materials decompose and researchers lose the ability to fully reconstruct the past. Therefore, the task of preserving organic remains is one of the most challenging for historians and archaeologists, as without proper conservation, many artifacts will forever disappear from our understanding of history. In this context, accurate documentation of finds is particularly important, so that even without the physical material, researchers have data for study. The concept of a technological signature of a civilization lies in the fact that each culture leaves a unique trace in history, which can be recognized through its achievements and characteristics. The technological signature encompasses both the level of development of tools and structures, as well as methods of labor organization and management. For example, it can be seen in how a society uses available resources, how it produces goods, and what forms of exchange it employs. Each element of this signature helps historians and archaeologists reconstruct the picture of life in the past, allowing them to understand which processes were formed in a specific culture. It is important to note that the technological signature can vary significantly between different civilizations, making it unique and capable of telling about the specific conditions of life and thought of people. This concept serves as a key to understanding how civilizations interacted with each other and with the surrounding nature, creating complex systems that we can study and analyze today. The technological signature also helps identify connections between different cultures and periods, making it possible to gain a deeper understanding of historical processes. Thus, each element, from architecture to agriculture, contributes to the overall picture, allowing us to better understand how societies developed and what factors influenced their evolution. Radioactive isotopes serve as long-term markers of human technological activity because they persist in geological layers for millions and even billions of years. For instance, carbon-14, used for radiocarbon dating, can remain in organic materials for up to 50,000 years. However, longer-lived isotopes such as uranium-238 and plutonium-24 can remain in the environment for millions of years, making them crucial for studying the long-term impact of human activity on the planet. Research shows that traces of these isotopes can be found in various geological layers, enabling scientists to track changes in ecosystems and climate caused by industrial activity. For example, increased levels of strontium-90 were found in deposits formed after mid-20th century nuclear tests, providing direct evidence of human impact on the environment. These data are not only useful in geology but also in archaeology, allowing us to determine when and how significant changes in technological activity occurred. Therefore, radioactive isotopes become important tools for understanding not only the history of our planet, but also the consequences of human activity that may be relevant for future generations. Studies conducted in various parts of the world show that isotope traces can point to specific events, such as nuclear disasters, and help assess their long-term impact on ecosystems. Synthetic materials and polymers are unique artifacts that can serve as long-term witnesses to technological civilization. These materials, such as plastic, do not decompose naturally and can persist in geological layers for millions of years. For instance, polyethylene, developed in the mid-20th century, can remain in the environment for hundreds of years, forming persistent layers in soil and oceans. Today, plastic makes up approximately 80% of all marine waste, and its traces can be found even in the most remote corners of the Earth. Research shows that in some places on the ocean floor, entire plastic islands are formed, where the concentration of synthetic materials exceeds natural sediments. These layers can be studied by geologists and archaeologists to understand how human activity has impacted the planet. Furthermore, polymers such as nylon and polystyrene may become important indicators of the Anthropocene epoch, when human activity has significantly altered ecosystems and climate. These materials form unique geological layers that can serve as true monuments of our civilization. For example, In the deposits that will form over the next millions of years, one can find not only remnants of synthetic substances, but also their interaction with organic materials, providing insights into how technologies have influenced life on Earth. It is worth noting that such synthetic layers may be more durable than many natural components, making them potentially valuable for future geologists and historians. Findings from these layers can provide a key to understanding how our civilization developed and how we interacted with our environment. Large-scale changes to landscapes and ecosystems, documented in the geological record, can serve as vivid traces of the existence of ancient civilizations. For instance, in Mesopotamia, where some of the earliest cities emerged, archaeologists have found evidence of irrigation systems that altered river courses and water abundance in the vicinity. These systems significantly impacted agriculture, as evidenced by the discovery of remains of crops like barley and wheat that were cultivated under these conditions. In ancient Egypt, construction projects such as the famous pyramids led to landscape changes. The construction required a vast amount of stone, resulting in the formation of quarries. This activity left traces that can be seen even from space. Additionally, in South America, on the territory of modern Peru, the Incas created terraces on mountain slopes, which contributed to changes in the ecosystem and increased crop yields. These terraces, which have endured for centuries, can still be observed and studied today. In Australia, indigenous peoples used controlled burns to manage vegetation, which also altered the ecosystem and is evident in the geological record. Such changes could leave traces in the form of coal deposits, which characterize specific periods and methods of resource management. Discoveries of such landscape and ecosystem changes not only attest to the activities of ancient civilizations, but also help understand how they adapted to their surroundings, opening new horizons for studying the interaction between humans and nature. It is important to note that these changes were not always sustainable. Some civilizations, such as the Maya, faced ecological crises due to overpopulation and resource depletion, which also left noticeable traces in geological layers. Scientific skepticism is a crucial tool in evaluating any unusual hypotheses and theories, particularly in the fields of history and archaeology. This approach involves critically examining claims rather than accepting them unquestioningly. Given that various cultural and historical phenomena can be interpreted differently, scientific skepticism helps to distinguish facts from fiction. For instance, if someone claims that there was a highly advanced civilization in Antarctica in ancient times, it is essential to thoroughly investigate the evidence before drawing any conclusions. This can involve analyzing archaeological finds, climate data, and historical records to determine the validity of such theories or whether they are merely products of imagination. Scientific skepticism does not mean rejecting all new ideas. Instead, it aims for an objective understanding of reality, which in turn opens the door to new discoveries and insights. This approach has become particularly relevant in light of recent archaeological findings that challenge established notions of civilization development, such as the discoveries in modern-day Iran, where traces of ancient settlements have been found, altering our understanding of human migration routes in ancient times. This underscores the need for critical analysis, as each new discovery can either confirm or refute existing theories. The principle of Occam's razor is named after the medieval philosopher William of Ockham, who argued that among competing hypotheses, the one requiring the fewest assumptions should be chosen. This approach, which is applied in various scientific disciplines, emphasizes that simplicity of explanation is an important criterion for its probability. For instance, if we have several theories about the causes of climate change, according to Occam's razor, we should choose the one that explains the observed phenomena most simply, without introducing additional, unproven factors. This principle is actively used in biology, physics, and other sciences, helping researchers avoid unnecessary complexity in their models. It is important to note that Occam's razor does not guarantee the truth of the simplest theory, but serves as a useful tool in the process of scientific inquiry. Thus, researchers can focus on models that are easier to test and confirm, which is particularly relevant in conditions of limited resources. Using this principle, many scientists have made breakthroughs in understanding complex processes, such as the evolution of species or the mechanisms of elementary particle physics, where each unnecessary variable can complicate the picture to such an extent that it becomes unclear. Occam's razor helps to eliminate unnecessary explanations, allowing researchers to focus on the most likely and simple causes. This approach was particularly relevant during the time when scientific theories about nature and society were just beginning to take shape and required clarity and precision. Extraordinary claims require extraordinary evidence, and this principle is particularly relevant in the context of hypotheses about ancient prehistoric civilizations. When discussing such civilizations as Atlantis or Lemuria, the amount of available historical and archaeological evidence is extremely limited. The scientific community demands compelling and irrefutable evidence, as such claims not only challenge traditional notions of human development, but can also fundamentally alter our understanding of history. For instance, if someone claims that the remains of a highly advanced civilization lie at the bottom of the ocean, it is not enough to present just photos or videos. Detailed reports on underwater research, findings of artifacts that can be dated, and identified as works of art or engineering are necessary. Without such substantial evidence, such hypotheses are perceived as speculative. Furthermore, many researchers emphasize that even if such civilizations did exist, their traces could have been destroyed by time, natural disasters, or human activity, making the task of finding evidence even more challenging. For example, in the late 20th century, research was conducted in the Baghdad area, where archaeologists discovered signs of complex sewage systems that could have belonged to ancient civilizations. But definitive proof that these systems were part of some lost culture has not yet been found. It is interesting that many such hypotheses resurface in popular culture, creating additional pressure on scientists who must respond to these challenges, but without strict scientific foundations. Such ideas typically do not receive official recognition. The complexity of the situation lies in the fact that each new discovery in archaeology requires a re-evaluation of previous knowledge, and therefore, any extraordinary claims about civilizations that existed before the advent of writing require not only thorough research, but also real, directly observed data. Modern scientific methods open up new horizons in the study of ancient civilizations, enabling researchers to analyze data with unprecedented accuracy and depth. These methods are based on a systematic approach to the study of artifacts and remains, which includes the use of statistical models for interpreting archaeological finds and identifying patterns that were previously overlooked. Thanks to interdisciplinary cooperation, historians, anthropologists, and geologists can combine their efforts to create comprehensive pictures of cultural interactions and migrations. Furthermore, new methods allow for the precise dating of finds, significantly improving the chronological context of events and objects. This opens up possibilities for a more detailed understanding of the social structures, economic systems, and technologies used by ancient peoples. Scientists can also analyze the surrounding environment to better understand how climate changes influence the development of civilizations and to assess which factors contributed to their rise or decline. All these aspects contribute to a more complete picture of human life in the past, which is undoubtedly important for understanding historical context and its impact on the present. For instance, in some cases, this can lead to unexpected discoveries about the significance of certain regions or resources that were previously not considered in traditional historical narratives. Research continues, and scientists continue to find new ways to conduct in-depth analysis, making each find more valuable and multifaceted. As a result, archaeological excavations are no longer just about finding artifacts, but a genuine investigation of complex networks of human interactions, cultural exchanges, and historical events. Currently, archaeologists have discovered numerous objects that shed light on the way of life of ancient people. Satellite mapping and LiDAR technology are opening new horizons in archaeology, enabling the discovery of hidden structures beneath the Earth's surface that were previously unnoticed. These technologies use lasers to scan the landscape, allowing for the creation of high-resolution three-dimensional maps. For instance, in Central America, archaeologists have used LIDAR to uncover extensive urban complexes that were hidden beneath dense jungles. Such findings, such as the remains of pyramids and roads, indicate the presence of complex civilizations with developed infrastructure. In Brazil, researchers have employed satellite mapping to study the Amazon rainforest, revealing a network of ancient canals and terraces which changes our understanding of human interaction with the environment. LIDAR also helps to identify the boundaries of ancient settlements, which may indicate their artificial origin rather than natural processes. Thanks to these technologies, scientists have gained the ability to reevaluate numerous historical events and migrations that were previously considered insignificant or non-existent. This not only deepens our knowledge of ancient cultures, but also raises new questions about how social and economic structures of these societies developed. For example, in Mexico, archaeologists have used LIDAR to uncover at least 100,000 new structures, including residential buildings and temples, which confirms the scale and complexity of ancient Mexican civilizations. The revelation of such details about human history becomes possible only due to modern technologies that continue to develop and open new horizons in the study of history. Methods of mass spectrometry and isotopic analysis have become the primary tools for determining the age and origin of materials in archaeology. Mass spectrometry allows for the study of sample composition by separating them into constituent substances based on mass, enabling precise identification of the elements present and their proportions. For instance, this method can detect the presence of carbon, which is used for radiocarbon dating to determine the age of organic materials up to 50,000 years. Isotopic analysis, on the other hand, focuses on the study of isotopes of elements such as carbon, oxygen, or strontium. This method helps determine the geographical origin of materials by analyzing the isotope ratios in samples. For example, differences in strontium isotopes can indicate the location where a particular product was grown, which is particularly important for understanding human migration and trade in ancient times. Unusual isotope ratios can also indicate technological processing of materials. Research has shown that certain processing methods, such as smelting or heat treatment, leave characteristic signatures in the isotopic composition, aiding archaeologists in reconstructing the technological processes used in the past. Therefore, the use of these highly accurate methods opens up new possibilities for detailed analysis of historical artifacts and understanding their context. In the year 2000, scientists from the University of California applied mass spectrometry to study ancient ceramic artifacts, which allowed them to determine that some of them were made from clay imported from other regions. Computer modeling and simulations have become essential tools in the reconstruction of ancient ecosystems and climatic conditions. With their help, scientists can recreate various climate change scenarios over thousands of years, analyzing how these changes affected the development of living organisms and human civilizations. For instance, researchers use models to assess how temperature and precipitation changes could have impacted agriculture in regions such as Mesopotamia or ancient Egypt. This allows us to determine when in human history climatic conditions were most favorable for agriculture and consequently for the growth of complex societies. Modeling ecosystems also helps us understand which plant and animal species could have existed in different climatic conditions, providing insights into how people interacted with their environment. For example, some studies have shown that during periods of higher humidity in Mesopotamia, new agricultural crops emerged, contributing to the development of the first cities. Using such models, we can also trace how climate changes influence the migration of peoples, which is crucial for understanding historical processes. Scientists can model how temperature fluctuations could lead to droughts or conversely, excessive rainfall, creating conditions for the rise or fall of civilizations. Thus, the application of computer modeling helps not only reconstruct the past, but also predict possible future climate change scenarios and their impact on humanity. This is particularly relevant in light of contemporary climate changes, as understanding historical ecosystems can aid in the development of adaptation strategies. The concept of the Anthropocene suggests that humanity has become a significant geological factor, capable of altering the environment on a global scale. This is not just about human impact on nature, but about how human activities shape ecosystems and climate conditions. For instance, large-scale deforestation for agriculture changes soil composition and biodiversity loss. The Industrial Revolution, with its massive carbon dioxide emissions, created conditions for global warming, which in turn affects sea levels and climate patterns. Water resources are being depleted, and planetary pollution has become the norm. It is important to note that anthropogenic changes do not only affect ecosystems, they also impact social structures, alter economic models, and generate conflicts over resources. Environmental catastrophes drive population migration, leading to new social challenges and requiring a reassessment of political strategies. In this context, understanding the Anthropocene becomes critically important for developing sustainable solutions that could minimize the negative consequences of human activity. One significant aspect is that the changes we observe today have long-term effects, and every step we take shapes the future of our planet. It is worth mentioning that the Anthropocene is not a static concept. It continues to evolve as humanity faces new challenges and threats. The plastic layer in sedimentary deposits has become a unique geological marker of human civilization, which will persist for millions of years after our disappearance. In geological layers formed in the 20th and 21st centuries, scientists have found not only microplastics, but also remnants of packaging, bottles, and other items used in everyday life. These discoveries indicate the enormous scale of plastic use. By the year 2200, humanity is expected to have produced over 800 million tons of plastic, with the majority of it ending up in the environment. Geologists believe that this layer will serve as one of the key indicators for future researchers studying our era, much like we study dinosaur fossils or the remains of ancient civilizations today. Plastic does not decompose, but breaks down into microplastics that can be found at great depths in the Earth's crust. These microplastics not only alter the composition of sedimentary rocks, but can also impact ecosystems, making their study relevant. In some places, such as oceanic trenches, the level of plastic pollution reaches catastrophic proportions, which is also reflected in geological records. The plastic layer can preserve traces of chemical additives, dyes, and other substances used in production, providing a precise picture of the technologies and consumption habits of our time. Research shows that this layer will be visible in the geological record for millions of years, making it a significant legacy that we leave behind. Global changes in the composition of the atmosphere serve as a clear indication of the existence of a technological civilization, and these changes will be recorded in the geological layers we leave behind. In ice cores extracted from polar regions, one can find air bubbles that preserve traces of gases released into the atmosphere over the past century. For instance, the concentration of carbon dioxide in the atmosphere has risen from approximately 318 parts per million in the 19th century to over 400 parts per million today. This increase is linked to the widespread burning of fossil fuels and deforestation. Analysis of these bubbles will enable future researchers to understand how human activities have affected the climate and ecosystems of the planet. Furthermore, studying gases such as methane and ozone will provide insights into agriculture, industry, and changes in lifestyle. In the ice sheets of Greenland and Antarctica, which preserve atmospheric samples, sharp changes in the concentration of pollutants like freons have been recorded, indicating the use of chemical substances in the 20th century. These data will not only help study the impact of humanity on the climate, but also understand the development of technologies and their ecological consequences. Therefore, ice cores will act as temporal capsules, recording changes in the atmosphere and providing valuable information about the technological civilization. In the future, when scientists analyze these samples, they will be able to reconstruct the picture of how humanity has influenced the climate over the centuries. Mass extinction of species caused by human activity will become one of the most conspicuous biological markers in the fossil record, easily identifiable by future researchers over millions of years. Currently, scientists are documenting a rapid decline in species. According to the World Wildlife Fund, approximately 30,000 plant and animal species go extinct every 10 years. This, for instance, future strategy. Additionally, DNA analysis of extinct species can help understand the causes of their disappearance and reveal patterns that could prevent further losses in the future. Scientific research shows that in some regions, such as the Amazon, the threat level to species has reached critical levels, which will also be reflected in the fossil record. In the future, when scientists study these layers, they will not only be able to document the facts of extinction, but also understand how humanity has influenced nature, leaving behind a trace that will be visible to the naked eye. Ultimately, the question arises, why do some civilizations undergo these cycles repeatedly, while others disappear forever? Perhaps this is related to their ability to adapt to changes, or conversely, to their rigidity in the face of new challenges. Throughout history, we see numerous examples where social, economic, and ecological factors have influenced the resilience of societies. For instance, it is noteworthy that each of these stories leaves behind lessons that, seemingly, should be learned, but often repeat themselves, as if humanity cannot escape its historical burden. These cycles not only reveal the vulnerability of human communities, but also prompt us to consider how contemporary societies respond to global challenges such as climate change, migration, or political conflicts. Understanding these processes can aid not only in studying the past, but also in attempting to predict the future. One such tragic example is the fall of the Roman Empire, where internal conflicts and economic problems led to its disintegration. Research indicates that many contemporary societies face similar challenges, raising the question of how to prevent the repetition of past mistakes. Ultimately, for example, the concept of the Great Filter from Fermi's theory posits a hypothetical barrier that hinders the development and long-term survival of technological civilizations in the universe. This idea emerged as an attempt to explain why we do not observe other intelligent beings, despite the vast size of our galaxy and the potential number of habitable planets. The Great Filter could be present at various stages of life's development. It might involve conditions necessary for life to emerge, such as the presence of water and essential chemical elements, or it could pertain to later stages when civilizations reach it. One of the most pessimistic assumptions is that most civilizations simply do not pass through this filter and disappear before they reach a level where they can colonize other worlds or establish contact with other intelligent beings. Some redevelopment. Self-destruction as the fate of technological civilizations that have reached a certain level of development is one of the most alarming concepts in contemporary science. Research indicates that highly developed societies may encounter internal conflicts, ecological disasters, or nuclear wars, which ultimately lead to their demise. For instance, civilizations like the Maya or Aztecs already faced issues of over-exploitation of resources, which led to their decline. Looking at a broader scale, one can find that every known civilization, from the Sumerians to the Romans, had moments when excessive ambition and technological progress resulted in catastrophic consequences. Some scientists propose that self-destruction could explain the absence of clear traces of ancient intelligent beings on Earth. If we assume that such civilizations existed but disappeared due to their actions, this could explain why we do not find artifacts confirming their existence. Further, it is important to note that such scenarios are not purely theoretical. The examples of Hiroshima and Nagasaki demonstrate how technologies can be used for self-destruction. These events remind us that even the most advanced civilizations can be on the brink of catastrophe if they cannot control their achievements. This idea is based on the fact that the planet's resources are limited, and for long-term survival, it is necessary to find ways to use them rationally. Sustainable development implies that humanity must learn to meet its needs without putting at risk the ability of future generations to meet theirs. Additionally, sustainable development includes principles of ecosystem management, which help preserve biodiversity and maintain the health of ecosystems, thereby enhancing resilience to environmental changes. Sustainable agricultural practices, such as crop rotation and organic farming, demonstrate how productivity can be increased without harming the land. Effective waste management, recycling, and reducing consumer behavior, all these are elements that can ensure harmony between humans and nature. The implementation of the sustainable development concept can allow civilization to exist for millions of years without encountering catastrophic consequences that arise from excessive resource exploitation. Space archaeology is a relatively new field that combines traditional archaeological methods with modern technologies, including satellite imagery and remote sensing. For instance, with the help of space technologies, archaeologists can identify ancient civilizations hidden under forests or sands and study landscape changes that may have influenced cultural development. This discipline opens up new horizons in understanding historical processes, allowing for more accurate reconstruction of the past and viewing it from a broader perspective. Space archaeology also aids in the preservation of monuments by providing data on the condition of objects and potential threats, such as erosion or urbanization. With its help, it is possible not only to identify but also to protect vulnerable historical sites, making it a crucial tool in the fight to preserve cultural heritage. Work in this area is carried out in various regions of the world, where satellite data is used to create three-dimensional models and maps, significantly accelerating the process of research and analysis. The search for artificial structures on the Moon has attracted the attention of scientists as a potential method for detecting traces of ancient civilizations. The lunar surface lacks erosion and tectonic activity, which on Earth over time destroy evidence of human activity. This means that any possible artifacts or constructions created by intelligence could remain in their original state for millions of years. For example, the most mysterious finding is what is known as the lunar city, which consists of a group of strange objects with clear angles and symmetrical lines. Additionally, the absence of an atmosphere on the Moon allows the details of such structures to be preserved in better condition than on Earth, where wind and water gradually erase traces. There are even projects to create automated research devices that will search for anomalies on the lunar surface that could indicate human or extraterrestrial presence. Thus, one of the most interesting aspects is the possibility of using new technologies, such as 3D scanning and analysis of satellite data, for a more detailed study of these areas. Scientific missions such as Curiosity and Perseverance are actively analyzing Martian soil and atmosphere, searching for organic molecules and traces of ancient microbes in clay deposits and sediments. Scientists believe that in the distant past, Mars had conditions similar to Earth, which could have allowed for the development of complex life forms. Additionally, high-resolution images obtained by orbital spacecraft allow for detailed geological studies and the identification of potential sites where remnants of life might have existed. The scientific community is actively discussing the possibility of ancient Martian civilizations based on mysterious structures that could resemble artifacts, although definitive proof is lacking. Recent findings in the crater Ezer, where sedimentary rocks are being studied, have also sparked interest, as these rocks could have formed under conditions favorable for life. Scientists suggest that some of these objects may have been manipulated by technologically advanced civilizations. For example, the asteroid Bennu, which is the target of the OSIRIS-REx mission, contains a large amount of carbon materials and organic compounds, making it potentially interesting for studying signs of technology. Research science, for instance, anomalies in the trajectories of some objects may suggest the influence of powerful forces, possibly used to change their course. Further, this aspect is actively studied by astronomers and astrophysicists who conduct observations and use spectroscopy to analyze the chemical composition of small bodies. For example, the O system, but also the potential technologies of other civilizations. In particular, the DART mission, launched by NASA, aims to change the course of the asteroid Dimorphos to understand if this is possible and what technologies could be used for such manipulations. For instance, in some scientific circles, there is discussion about creating artificial magnetic fields to protect planets from solar wind, which could be crucial for preserving atmospheres. Some scientists point to risks associated with altering natural processes, while others emphasize the necessity of such actions in the face of global climate change on Earth. This has sparked scientific and philosophical debates about how far humanity is willing to go in its attempts to control nature. In recent decades, interest in planetary engineering has significantly increased, driven by technological advancements and the pressing challenges humanity faces, such as climate change, resource depletion, and population growth. These challenges require new solutions that could be provided within the framework of this concept. Research in this field is conducted worldwide, and many scientists believe that in the future, planetary engineering could become a vital tool for addressing global problems. Specifically, some projects involve using biotechnology to create organisms capable of surviving in extreme conditions on other planets, which would enable the colonization of new worlds and provide humanity with essential resources. Scientific research in this area is actively progressing, and there are already patents for various methods that could help achieve these goals. Terraforming is a deliberate process of altering the climate and ecosystems of a planet to create conditions suitable for life. This is a complex and multi-stage process that involves changing the atmosphere, temperature, landscape, and even the biosphere of the planet. For example, to terraform Mars, scientists propose heating its surface to melt the polar ice caps and release carbon dioxide, which would create a denser atmosphere and raise the temperature. As a result, conditions for the existence of liquid water could emerge, which is a key element for life. However, terraforming is not limited to planets. It can also be considered in the context of altering ecosystems on Earth. For instance, efforts to restore forests and create new water bodies can significantly change the local climate and biological diversity. Such changes, in turn, can leave long-lasting geological traces. Increasing the area of forests will not only alter the composition of the atmosphere, but also the structure of the soil and affect the hydrological cycles of the region. This will lead to the formation of new layers of sedimentary rocks, which will be recorded in the geological record. If we consider large-scale terraforming projects, they could induce changes in tectonic activity, which would also affect the geological structure. Furthermore, if genetically modified organisms are used in the process of terraforming, this could lead to the creation of new ecosystems that may significantly differ from natural ones. These changes could be so profound that future generations of scientists will study them as separate geological epochs, much like how we currently study the epochs of the Ice Age or the evolution of dinosaurs. Advanced civilizations, such as those that may exist on other planets, or in the distant future on Earth, are capable of creating megastructures that leave clear traces in the geological record. One example of such structures are artificial satellites, which can be not only simple spacecraft, but also complex systems with orbital rings capable of accumulating solar energy or supporting orbital life. For instance, the concept of orbital rings envisions the creation of massive structures that rotate around a planet, similar to Saturn's rings, but made of synthetic materials. These rings could serve both as sources of energy and for transporting resources between planets. Another intriguing project is the space elevator, which consists of a long cable connecting the planet's surface to a geostationary orbit. This elevator could revolutionize access to space, reducing launch costs, and would leave significant archaeological traces in the form of anchor stations. If such a civilization were to disappear, its megastructures would serve as evidence of its existence, remaining as debris that future researchers would study, much like we currently study the remains of ancient civilizations. Such structures could even influence the climate and ecosystems of a planet, creating long-term changes in the landscape and atmosphere. For example, the shadows cast by orbital rings could affect surface temperature, altering climatic conditions. As archaeologists studying such objects might discover materials with no earthly counterparts, further indicating the high technological level of their creators. Fractal architecture is based on mathematical principles where forms repeat at different scales, creating visually complex but harmonious structures. For instance, buildings can resemble natural formations such as trees or mountains, utilizing geometric patterns found in nature. These technologies enable the design of structures that blend seamlessly with the environment, making them practically indistinguishable from natural forms. Architects employ such methods to create sustainable and eco-friendly buildings that not only look attractive, but also perform functions characteristic of living systems. As a result, fractal and biomimetic approaches can lead to the creation of cities that are integrated into ecosystems, making it challenging to identify these objects as artificial. These technologies are already being applied in some modern architectural projects, such as the greenhouse in Copenhagen, which uses biomimetic principles to optimize resource usage. Cultural blindness is a phenomenon where people fail to notice or recognize cultural differences around them. This can manifest in the disregard of local customs, traditions, or even the misunderstanding of the meanings embedded in various cultural practices. Often, cultural blindness arises from a lack of experience or education, leading to a distorted perception of the world. People may perceive their own culture as the only correct one, and fail to acknowledge that other societies have their unique approaches to life, which can be just as logical and justified. This cultural blindness can also limit personal growth and development, as an individual who is not open to learning new things loses the opportunity to learn from others and broaden their horizons. In the study of history and sociology, this concept helps understand how biases and stereotypes can influence the perception of other peoples and their achievements. For instance, this results in a superficial understanding of historical processes and cultural interactions, which in turn can distort the overall picture of human history. For instance, confirmation bias leads researchers to seek and interpret information in a way that confirms their existing beliefs, while ignoring facts that could refute their theories. This is particularly evident in archaeology, where many specialists adhere to traditional views on the development of civilizations, making it difficult to accept more daring hypotheses, such as the existence of highly advanced technological cultures in prehistory. Additionally, the group effect can cause scientists working in a particular field to unconsciously avoid discussing unconventional ideas to avoid questioning their professional positions and relationships with colleagues. This results in even well-founded theories about lost civilizations, which could change our understanding of history, being marginalized in scientific discourse. For example, findings that suggest complex technologies, such as metalworking or the construction of megalithic structures, are often criticized and rejected if they don't fit into conventional timeframes. Furthermore, attachment to methodology and traditions can limit research boldness, leading to the neglect of alternative information sources. Scientists who attempt to present evidence for the existence of prehistoric technological civilizations face skepticism and disbelief, creating a closed loop where innovative ideas are not given proper attention. For instance, the theory that some megalithic structures could have been built using lost technologies is often dismissed as fantasy, despite the existence of many artifacts that could support such ideas. Consequently, many important aspects of our history remain unexplored because the scientific community is not ready to step beyond familiar paradigms. Anthropocentric bias in science manifests in the fact that we consider the human path of evolution as the only possible one, without taking into account alternative forms of intelligence and technological development. There is a belief that only humans are capable of complex thought, abstract reasoning, and technological creation, but such assertions ignore numerous examples in nature. For instance, these examples show that intelligence can take various forms, different from human intelligence. Furthermore, many cultures and civilizations that existed long before us could develop their own technologies and systems of knowledge, which we either do not understand or do not acknowledge. For example, the Incas created sophisticated systems for managing water resources and architecture that served them for nearly 1,000 years. However, in our era of dominant scientific approach, we often try to fit everything into a single mold. Human achievements become the standard, while the achievements of other species remain unnoticed. This approach sets certain boundaries within which we strive to understand the world, but it does not allow us to see its diversity. Thus, even when we consider artificial intelligence, its development is often compared to human intelligence, which is also biased. In this context, it is important to remember that various forms of intelligence can coexist and develop in parallel, and this creates immense opportunities for study. Understanding that intelligence can be diverse opens new horizons for scientific research and understanding our place in nature. Ultimately, anthropocentric bias not only limits our understanding, but can also hinder progress in science, as we overlook potential alternatives that could enrich our knowledge of the world. As a result, under the influence of this bias, we continue to ignore facts that could change our understanding of the development of intelligence and technologies in general. For example, some studies claim that many animals are capable of learning and knowledge transfer, which challenges our notion of a single path of evolution of reason. For instance, if we discuss ancient cultures like the Incas or Mayans, we immediately imagine their stone structures and agricultural technologies. However, there is a possibility that other, more advanced societies could have used materials and energy sources that we simply cannot recognize. We may overlook the traces of a civilization that utilized biological technologies, such as genetic modification of plants for food or energy sources based on biotechnology, like converting solar energy using special organisms. If such a civilization existed, its artifacts might look completely different. Instead of the familiar tools, we might find only traces of biochemical processes. We might miss entire epochs and achievements simply by not knowing what to look for. Our contemporary science is often not ready to accept ideas that contradict established norms. For example, the study of such alternative technologies opens new horizons that could change our perception of historical processes. For example, in ancient China, gunpowder was used not only for weapons, but also for creating various mechanisms that could serve as a source of energy. We cannot exclude the possibility that there were once civilizations that used biomechanical systems entirely different from anything we know. Artifacts found in various regions of the world, from South America to Asia, may indicate that we do not have a complete understanding of how these societies functioned. In this context, every discovery, even the smallest one, can open a window into a world that we cannot imagine, and this underscores the need to rethink our approaches to the study of history and archaeology. For example, recently in Peru, remains of structures were discovered that, according to researchers, could have been used for transmitting energy through vibrations, which is completely outside our understanding of ancient technologies. The concept of the parallel technological path opens up intriguing prospects for research, suggesting that the development of technologies in different cultures could have followed a different, less familiar trajectory. This implies that isolated peoples could independently develop unique methods and technologies that did not intersect with those known to us from history. For instance, while one civilization might have focused on the development of metallurgy, another could have pursued the use of organic materials or more complex natural processes. This diversity of approaches is astonishing, as it challenges traditional notions that technological progress inevitably moves along a single line. Instead, one might hypothesize the existence of numerous technological islands, each developing at its own pace and in its own direction, leading to a wide variety of ways to address similar problems. Such a perspective on the history of technologies can alter our understanding of how humanity interacted with the surrounding world and what knowledge it accumulated. In this context, it is important to consider that different cultures could draw on their unique sources of inspiration and resources, resulting in the creation of entirely different technologies. Research indicates that such parallel paths could have existed not only in antiquity, but also in later historical periods, when independent scientific discoveries and inventions were made in different parts of the world. For example, this paradigm shift in the perception of technological history underscores that we can only glimpse the curtain over a multitude of alternative paths that humanity could have taken. In some cases, these alternatives could be more effective or even more eco-friendly than the solutions we are familiar with. Research in this field continues to uncover numerous unexpected facts and discoveries that may one day change our understanding of technological progress throughout history. In such conditions, it becomes clear that each culture, regardless of time and place, made a unique contribution to the overall process of accumulating knowledge and technologies. For instance, in South America, the Incas created a complex network of roads and bridges using only natural materials, demonstrating a deep understanding of local ecology and available resources. If civilizations had chosen a biotechnological path of development, we might observe a completely different picture of progress. Instead of mechanical technologies, which leave noticeable archaeological traces, such as factories and machines, societies could have focused on creating modified organisms capable of performing functions that today we attribute to technology. For example, instead of tractors that till the fields, there could have been genetically modified plants or animals capable of performing agricultural work independently, significantly reducing the need for heavy machinery. This concept is not new. In cultures such as ancient Chinese, early experiments with the selection of crop plants and animals took place, which laid the foundation for more complex biotechnologies. In such a scenario, biotechnology could have become the main driver of scientific progress, allowing the creation of organisms that not only adapted to changing environmental conditions, but also altered them to their advantage. For instance, since such organisms would not leave behind traditional traces, archaeologists might face the challenge of determining the level of technological development in such civilizations. Instead of rusted machine parts, we would have to search for signs of biological changes in ecosystems, which would require a completely new approach to the study of history. In this context, one could recall ancient legends and myths where living beings possessed extraordinary abilities, perhaps reflecting a deep understanding of people's interaction with nature and the creation of new forms of life. Such an approach could lead to the creation of sustainable ecosystems that restore themselves, which in turn would change the appearance of traditional agriculture and production, making them more harmonious with nature. Humanity could have focused on symbiosis with nature rather than its conquest, leading to a more balanced societal development. In such a case, modern engineering might appear as an outdated legacy, rather than the foundation of progress. Modern scientific achievements in the field of genetic engineering, such as CRISPR, only confirm that the possibility of creating new forms of life lies at the surface. For example, using this technology, scientists have already modified rice to make it more resistant to drought, demonstrating how biotechnologies can change our understanding of food security and resilience. Quantum technologies represent a field that has the potential to revolutionize our understanding of ancient civilizations and their capabilities. Some scientists suggest that in the distant past, civilizations existed that could manipulate fundamental forces of nature using principles of quantum mechanics. For instance, research indicates that quantum entanglement and superposition could have allowed ancient people to interact with matter at levels beyond our current comprehension. This implies that such civilizations could have created energy fields or altered material properties without leaving behind physical artifacts, making their traces nearly invisible to archaeologists. One often discussed example in scientific circles is the possibility of using quantum technologies to create indestructible structures or even manipulate space and time. In this context, it is worth noting the myths and legends of many cultures that describe phenomena similar to quantum effects, such as instantaneous movements or creation from nothing. These stories may reflect real knowledge of quantum principles that have been lost over time. The question of whether any ancient civilization could have reached such a level of understanding of nature remains open, but the very discussion of such possibilities prompts us to consider the depth of human potential. It is important to note that many modern technologies, such as quantum computers, are based on principles that may have been known in the past. For example, quantum superposition allows for computations at incredible speeds, which could be analogous to the technologies we discuss in the context of ancient civilizations. Research in the field of quantum mechanics continues to advance, and perhaps one day we will be able to look into the past and understand how ancient people could have used knowledge of quantum phenomena. Currently, archaeologists continue to search for evidence that could either confirm or refute these theories. In a major study conducted in the early 2000s, scientists discovered ancient textual records that may indicate the existence of knowledge about certain quantum principles, although with a significant degree of interpretation. Among the immaterial technologies that could develop in intelligent beings, those based on information and consciousness, leaving no physical trace in the geological record, are particularly intriguing. For example, imagine a communication system based on the transmission of thoughts or emotions through mental impulses, which could be characteristic of a highly advanced civilization capable of interacting at the level of collective consciousness. Such a method of communication would not require physical objects and could be extremely efficient, allowing the exchange of complex concepts instantaneously. Additionally, technologies for manipulating consciousness, which would enable intelligent beings to alter their perception of reality and create virtual worlds accessible only to them, could be considered. These worlds could exist solely in their consciousness, leaving no traces in the physical world, but exerting a significant influence on their culture and way of life. The widespread use of such technologies could lead to the creation of unique forms of art based on sensory perception, where each emotion and thought becomes an independent work, transmitted through collective consciousness. Furthermore, the concept of developing moral and ethical systems that could be passed down from one generation to another, not through written or oral sources, but through shared mental practices and collective experiences, could be explored. This would allow the preservation of knowledge about behavior and interaction without the need for physical artifacts such as books or monuments. Another aspect of such technologies is the possibility of creating complex mental models that would enable the prediction of the behavior of the surrounding world and decision-making based on collective experience, without fixing them in a physical format. For instance, such beings could develop methods for predicting weather or other natural phenomena based on joint observations and mental analysis, which would also leave no traces in the geological record. All this information could be transmitted through special rituals or states of consciousness that are not fixed in material objects, but can have a significant impact on the development of culture and social structures. In such a context, intelligent beings could create an entire network of immaterial knowledge based on the interaction of consciousness, opening new horizons for understanding their existence. The concept of planetary consciousness offers an intriguing perspective on the interconnectedness between all living beings and their environment. This notion suggests that Earth, as a unified system, possesses its own consciousness, in which each form of life plays a unique role. For instance, ecosystems function as complex networks where every living organism influences others and its habitat, creating interdependencies that are hard to overestimate. In this context, one can argue that the actions of one group of organisms can have far-reaching consequences for the entire planet, from climate change to the formation of the biosphere. This is particularly evident when considering human activity, Deforestation, water pollution, or altering natural landscapes not only affect local ecosystems, but also impact global ecological processes. For example, deforestation in the Amazon not only leads to the loss of unique species, but also reduces the oxygen level in the atmosphere, which can in turn provoke climate changes on other continents. Thus, planetary consciousness can be seen as a collective intelligence that emerges from the interactions of all living beings on Earth. While we may not always be aware of this consciousness, its manifestations are clear in how humanity influences the planet. It is important to note that understanding this concept can change our approach to ecology and our interaction with nature, emphasizing the need to care for our planet as a single, integrated organism where every cell has significance. In this context, the question arises: how can we contribute to the harmonious coexistence of all life forms on Earth? In this sense, studying interactions at the ecosystem level becomes particularly important, as they demonstrate how various natural elements can coexist in symbiosis, creating conditions for sustainable development and prosperity. There are numerous examples of such interdependencies, where one living being supports another, providing mutually beneficial conditions for existence. For instance, bees pollinate plants, enabling them to reproduce, while plants, in turn, provide food for bees. This interdependence shows how interactions at a small scale can influence the global balance. The Gaia hypothesis, proposed by British scientist James Lovelock in the 1970s, posits that Earth functions as a single, self-regulating organism, where living beings and the environment are in constant interaction and interdependence. Lovelock arrived at this idea by observing how the biosphere influences climate, atmospheric composition, and even the oceans. For instance, plants absorb carbon dioxide and release oxygen, supporting the life of animals that, in turn, release carbon dioxide necessary for photosynthesis. This concept suggests that Earth is not merely a passive stage, but an active participant in maintaining conditions favorable for life. The Gaia hypothesis also raises the question of possible planetary forms of intelligence, implying that Earth might be perceived as something more than just a biosphere. Some researchers consider the possibility that if Earth is capable of self-organization and regulation, it may possess a level of consciousness or intelligence, similar to how cells in a living organism work together to sustain life. This sparks intriguing discussions about the nature of intelligence and consciousness, as well as how we, as a human race, interact with our planet. For example, if Earth indeed behaves like an organism, our interference with its ecosystems can be seen as diseases that threaten its health. This leads to important reflections on how we can manage natural resources more responsibly and minimize our negative impact. Lovelock emphasizes that to understand these processes, one must consider not only biological, but also physical, chemical, and even astronomical aspects, as they all interact with each other. In this context, it becomes clear that merely observing nature is not enough. A deep understanding of the complex systems that make up our planet is required. Given all this, it is significant that the Gaia concept serves as a foundation for discussing the sustainability and future of Earth in light of contemporary environmental challenges. Lovelock also proposed that humanity should learn to work in harmony with nature, rather than against it, to ensure its survival. Microbiological collective intelligence is a hypothetical form of consciousness that emerges from the interaction of trillions of microorganisms inhabiting our planet. These microorganisms, including bacteria, archaea, and fungi, form complex ecosystems, interacting with each other through chemical signals and the exchange of genetic information. In some cases, they can coordinate their actions, creating an effect similar to a neural network, where each individual organism can be considered a neuron, and their interactions as synapses transmitting information. For instance, in soil, there is an exchange of substances between fungi and plants, allowing them to effectively use available resources and protect themselves from pathogens. Research shows that such interactions can be quite complex. Some bacteria can communicate with each other by releasing molecules that act as chemical signals, influencing the behavior of their neighbors. This interconnectedness and communication can create something more than just the sum of the behaviors of individual organisms. They can form a kind of collective consciousness, where information is processed and stored in the biosphere, much like it is in the human brain. In this context, microbiological collective intelligence opens new horizons for understanding ecosystems and their resilience. For example, in coral reefs, symbiotic relationships between corals and zooxanthellae represent a case of how microorganisms can work together to create a stable and diverse ecosystem. Each group of microorganisms can contribute to the overall health of the ecosystem, influencing its resilience to climate change and other stressors. There are, for instance, when nutrients are scarce, some bacteria can activate genes that help them survive by altering their metabolic pathways and thus adapting to the new environment. This ability to adapt and interact could be the foundation for a deeper understanding of ecosystem processes and their reactions to anthropogenic changes. Fungal mycelial networks represent an extraordinary example of a natural communication system capable of transmitting information over long distances. These underground networks, composed of thin threads called mycelia, have existed for hundreds of millions of years and facilitate connections between plants and other organisms. For instance, a study conducted in the 2000s revealed that fungi can transmit carbon from one tree to another, allowing plants to exchange resources and even warn neighbors of the presence of pests. These networks can cover large areas, connecting plants over distances of several kilometers. This discovery underscores the diversity and complexity of life beneath the Earth's surface. Mycelial networks function as a kind of internet, enabling organisms to transmit information about the state of their environment, as well as the presence of nutrients and threats. In some cases, such as when interacting with trees, fungi can even influence the growth and health of plants, providing them with necessary substances in exchange for carbon obtained through photosynthesis. Research also shows that certain types of fungi can respond to stressful conditions like drought and transmit signals to other plants, helping them adapt to changing conditions. This form of communication is based on chemical signals and electrical impulses that fungal mycelia use to transmit information. Mycelial networks are not only a crucial element of ecosystems, but also a potential foundation for understanding broader natural communication systems that have existed in the world for millions of years. In recent years, scientists have increasingly turned to mycelial networks as a model for studying complex interactions between living organisms and their habitats. Such research opens new horizons for understanding ecosystem processes and their interconnections, thereby highlighting the importance of fungi in maintaining the health of the planet. Temporal chauvinism is a concept that implies the belief that one's own epoch or time period is the highest and most significant compared to others. This phenomenon manifests in various spheres, including culture, science, and even everyday life. People often tend to consider their current achievements and views as the culmination of everything that came before, while past eras are perceived as less developed or irrelevant. Temporal chauvinism can be seen in the perception of historical events, where certain facts or achievements are unquestioningly placed above others, ignoring the context and uniqueness of each historical period. This leads to the distortion of historical narratives and the formation of stereotypes about the past. For example, some contemporary researchers may condemn the decisions and actions of people from the past without considering their living conditions and level of knowledge. In this context, it is interesting to note that temporal chauvinism can obscure a genuine understanding of the historical process, as each epoch, regardless of its achievements, has left an indelible mark and has its own strengths and weaknesses. There are views that temporal chauvinism not only affects the perception of history, but also the formation of identity, as people often use their cultural and historical affiliation as a tool for self-determination. Numerous examples from history show how views on the past are shaped under the influence of current ideologies and social changes. In this context, it is worth considering how we perceive our own history and how this influences our understanding of the present. Temporal chauvinism, therefore, is not just an academic term, but an important aspect that requires careful study and critical analysis to avoid a one-sided view of the processes that have shaped humanity over the centuries. Belief in the superiority of one's own time can lead to the simplification and ignoring of complex interconnections in history, making it necessary to delve deeper into the past and recognize our connection to it. Modern people often perceive past epochs as less developed and primitive, which can be a result of entrenched stereotypes and a lack of information. For instance, many believe that ancient civilizations could not achieve high levels of technological progress based on limited views of life in the past. However, if one looks at the achievements of peoples such as the Sumerians, Egyptians, or Maya, it becomes clear that they possessed a complex system of knowledge and technologies. For example, the Sumerians were the first in the world to invent the wheel and create writing, which allowed them to record information and develop trade. Egyptians built monumental pyramids using precise mathematical calculations and complex mechanisms. The Maya made significant advances in astronomy, developing calendars that accurately predicted solar and lunar eclipses. These examples demonstrate that ancient civilizations possessed highly developed knowledge and skills that are often ignored or underestimated by contemporary researchers and the general public. It is important to note that many cultural achievements of antiquity, such as architecture, art, and science, not only served practical purposes, but also reflected a deep understanding of the world and humanity. For example, the temples of ancient Greece were not just places of worship, but also demonstrated mastery in architecture and an understanding of proportions. Comparing them with modern achievements may seem appropriate, but it is important to remember that each epoch had its unique conditions and context that influenced the development of society. Current research shows that many ancient cultures exchanged knowledge and technologies, which contributed to their development. Such examples underscore that oversimplified views of the past can lead to misunderstandings and limit our understanding of historical processes. Archaeological finds continue to amaze scientists and challenge established views of history. For instance, in the year 2000 in Iraq, an ancient library was discovered with tablets containing complex mathematical and astronomical records. There are also traces of highly developed civilizations in places where their existence was considered impossible, such as Antarctica, where mysterious structures are found that may indicate human activity in the distant past. The history of humanity is not linear, but cyclical. Over millions of years, civilizations have risen and fallen on Earth, and this has happened in various forms. For instance, over the past 5,000 years, we have witnessed the rise and fall of great empires like the Roman and Ottoman, leaving behind only ruins. Scientists suggest that such cycles may not only occur within the framework of a single civilization, but also on a more global scale. The geological history of the planet shows that in different epochs, the climate changed, leading to mass migrations of peoples and the decline of cultures. For example, due to ice ages and global warming, entire nations abandoned their lands in search of more favorable living conditions. This is confirmed by archaeological finds in the territories of modern Kazakhstan and Mongolia, where archaeologists have discovered traces of migrations of nomadic peoples caused by climate changes. Furthermore, cycles of rise and fall can be linked to technological progress. Each new technology, from the invention of the wheel to the internet, can fundamentally transform society, but over time, even the most advanced technologies become obsolete, which in turn can lead to decline. For example, the Maya civilization achieved significant success in astronomy and mathematics, but by the 10th century, their culture had declined, despite their high level of development. Thus, history shows that technological societies can rise and fall repeatedly, leaving behind only artifacts and ruins. However, this is speculation about the future, while the facts of the past already indicate that the cycles of history are unchanging. Research shows that over the last 2 million years on Earth, there have been at least 25 ice ages. The concept of forgotten knowledge reveals to us the dark horizons of human history, where knowledge and achievements of civilizations could be lost forever. One of the reasons for the loss of information about past cultures is global catastrophes, such as volcanic eruptions, earthquakes, or even meteorite impacts, which could destroy entire cities and erase their achievements. For instance, the famous eruption of the Krakatoa volcano in 1883 led to catastrophic consequences, not only destroying ecosystems, but also hindering access to information about local cultures. Population migrations also played a role in this process. When peoples moved in search of more favorable living conditions, they often left behind not only their achievements, but also knowledge passed down through generations. For example, the disappearance of the Maya civilization may be linked to climate changes and resource shortages, leading to mass migrations and the loss of critically important information about city building, agriculture, and preserving traditions. Cultural collapses, such as the fall of the Roman Empire, also contributed to the loss of knowledge. With the collapse of centralized management, many technologies and cultural practices were forgotten, and written sources that could have preserved these knowledge were often destroyed or lost. As a result, many achievements of ancient civilizations, such as production technologies, construction methods, and even medical practices, became part of the forgotten heritage that may never be restored. Archaeological excavations sometimes bring only fragments of information that do not allow us to form a complete picture of how our ancestors lived and what knowledge they could have passed on to us. For example, in 2006 in Iraq, thousands of cuneiform tablets were discovered, but many of them were damaged, making it difficult to understand the entire body of knowledge related to the Sumerian civilization. Cosmic consciousness is a concept that encompasses a state of awareness that transcends individual perception. It implies a deep connection between humans and the universe, where each element of nature is perceived as part of a whole. This state allows people to recognize their role in a broader context, understanding the interdependence between all living beings and their environment. Cosmic consciousness is often associated with a sense of unity and harmony, where personal concerns and worries lose their significance in the face of global processes. Interestingly, this state can arise at various points in life, whether through art, science, or even everyday observations of nature. People experiencing cosmic consciousness may feel a surge of inspiration and a desire to act for the benefit not only of themselves, but of all humanity. For instance, many scientists studying the laws of physics or biology describe moments when they felt part of something greater during their discoveries. In such moments, they may realize that their work influences the future of the world. This realization can become a powerful driver for personal growth and socio-cultural progress. At the same time, cosmic consciousness can manifest in philosophical contemplations about the nature of existence, sparking intriguing discussions about humanity's place in the universe and its responsibility towards it. It is important to note that the perception of cosmic consciousness can vary among individuals, and its interpretation depends on personal experience and cultural background. For example, some may perceive it as a spiritual awakening, others as a scientific quest, and still others as a simple need to understand one's life in a broader context. It is worth noting that achieving this state is not always easy, and many people spend their entire lives seeking ways to connect with this higher level of awareness. However, even brief moments of connection with cosmic consciousness can significantly alter one's perception of the world and their place in it. Scientists also emphasize that such states can foster creative thinking and innovation, opening new horizons for scientific and cultural achievements. The hypothesis of panspermia suggests that life on Earth could have originated from extraterrestrial sources. This theory posits that microorganisms or organic molecules could have been delivered to our planet via meteoroids, comets, or cosmic dust. Research indicates that some microorganisms can survive in the harsh conditions of space, including extreme temperatures and radiation. For instance, the bacterium Deinococcus radiodurans, known for its radiation resistance, could theoretically survive a journey through space. This opens intriguing possibilities for understanding how life might have developed on other planets and then intersected with Earth. Moreover, panspermia is linked to the idea of ancient intelligent beings capable of interstellar travel and seeding life on various planets. Some theories suggest that such civilizations could have created conditions for the emergence of life similar to that on Earth. For example, if a highly advanced civilization could indeed control genetic material, it might send it into space with the intention of colonizing other worlds. Such ideas gain support from findings like organic molecules discovered on comets and asteroids, which could be precursors to life. Scientists also study exoplanets in the habitable zone, where conditions are similar to Earth's, and consider the possibility that life might exist or have existed there. In some cases, analyzing ancient texts and mythologies can reveal references to divine beings or extraterrestrials that might be connected to this hypothesis. Some researchers even connect panspermia with legends about UFOs and possible encounters with extraterrestrial life over the centuries. There are various viewpoints on this matter, and each adds its own layer to the complex picture of our understanding of the origin of life. The scientific community continues to actively investigate this topic, utilizing data from astronomy, biology, and even archaeology to answer the question of the true nature of life on Earth. The concept of cosmic intelligence posits the existence of a hypothetical form of consciousness that can be distributed throughout the entire universe and manifest in various material forms on different planets. This idea is based on the assumption that intelligence is not a unique property of humans or Earth-based life, but rather a universal characteristic that can emerge in the most unexpected corners of the cosmos. For instance, some scientists believe that on planets with conditions similar to Earth's, intelligent life forms capable of developing technology and culture could arise. Other theories consider the possibility of the existence of forms of intelligence that are not tied to biology, such as artificial intelligence or even quantum entities, capable of perceiving and processing information at levels beyond human comprehension. In such concepts, intelligence may not simply be a result of evolution, but rather a cosmic phenomenon that permeates all matter and energy in the universe. This opens up new horizons for understanding life. Perhaps intelligence is not an isolated phenomenon, but a part of a broader structure that connects all existing forms of life and matter. For example, in ancient Greek philosophy, there was a concept of the world soul, which encompasses all that exists, which resonates with modern ideas about cosmic intelligence. This concept is also reflected in some religious teachings, where it is said that all living beings are united through some higher consciousness. Research in the fields of astrophysics and exobiology raises questions about how intelligence can adapt to various conditions of existence, how it can evolve under the influence of the surrounding environment, and what forms it can take depending on the physical laws of a specific planet. There are even suggestions that intelligence could be transmitted through intergalactic interactions, similar to how energy is transmitted through space. In this context, cosmic intelligence becomes not just an abstraction, but a real subject of research that could lead to new discoveries about the nature of consciousness and existence in general. Some researchers even suggest that we may be on the verge of discovering new forms of intelligence that could not only change our understanding of life, but also reveal the mysteries of the universe. Quantum entanglement is a unique phenomenon that could serve as the foundation for information exchange between intelligent beings over vast cosmic distances, bypassing traditional communication technologies. This phenomenon was first described by Albert Einstein, whom he referred to as spooky action at a distance. The essence of quantum entanglement lies in the fact that two or more particles become linked in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. For instance, if one particle changes its state, the other will change immediately, even if it is located millions of light years away. This opens up boundless possibilities for communication, as information transfer does not require time, unlike traditional communication systems based on radio waves or light signals. Research indicates that such transfer could be employed to create a new type of quantum communication, which would be safer and faster than existing methods. Scientists also consider the possibility of using quantum entanglement to create networks that could connect intelligent beings across various corners of the universe. Such an approach could lead to the creation of a system where information is transmitted instantaneously and securely, making communication over cosmic distances not only possible, but also reliable. Experiments conducted in laboratories have already demonstrated that quantum entanglement can be used for information transfer over distances of several kilometers, and with the advancement of technology, this distance will only increase. Scientists hope that in the future, quantum entanglement will serve as the basis for a system that allows for the exchange of knowledge between civilizations that may exist in the most remote corners of the galaxy. Research in this area continues, and scientists are constantly seeking new ways to utilize quantum mechanics to enhance information transfer. Ancient civilizations have always fascinated both scholars and the general public because they represent not only the achievements of the past, but also reflections of human nature and aspirations. The question arises, what drives people to create complex societies, architecture, and systems of governance? It is intriguing that many of these civilizations, regardless of their geographical location, developed unique approaches to organizing life and interacting with the world around them. For instance, in ancient Egypt, pharaohs were not just rulers. They were considered divine beings, which allowed religion and politics to be integrated into a single system, strengthening power and stability. In Mesopotamia, the first forms of writing, such as cuneiform, emerged, which became the basis for documenting laws and record-keeping, thereby ensuring transparency and order in society. On the other hand, ancient Indian and Chinese civilizations laid the foundations for philosophy and science, creating systems that sought to explain humanity's place in the universe and its connection to nature. These approaches reflect deep contemplations on life and death, justice and morality, and how to build a society where each person has their place and significance. Ancient Greek city-states, for example, developed ideas of democracy, which challenged traditional authoritarian models of governance. All these examples demonstrate that civilizations did not merely exist, but also posed questions for which they sought answers, creating unique cultural codes. Nevertheless, despite their differences, many of them faced the same challenges, such as wars, natural disasters, and internal conflicts, which could either destroy or transform their societies. This dynamism allows us to see how humanity reflects its aspirations and fears in its cultural achievements, and how, despite time and place, the same themes continue to recur in history. Therefore, studying these ancient civilizations enables us not only to understand their achievements, but also to delve into the depths of human nature, which strives for self-expression and understanding of the world around it. In archaeological excavations, artifacts such as stone tablets with inscriptions or everyday items are often found, which provide insights into the daily lives of their inhabitants. When analyzing the hypothesis of multiple occurrences and disappearances of intelligent life on Earth, existential questions arise that touch upon the very essence of our existence. What is the probability that intelligent beings existed on our planet before us? If such civilizations did exist, what happened to them? Were they destroyed by natural disasters, or did they perish due to wars and conflicts? These questions prompt important reflections on the fragility of life and how quickly it can disappear if it does not learn to adapt to changes in its environment. Additionally, there arises the question of how we can avoid the fate of previous civilizations. What can we do to prevent our society from repeating their mistakes? Is it meaningful to study their possible achievements and errors to draw lessons? It is also important to ask what makes us unique in such a case. Is our capacity for self-awareness and reflection on the future a guarantee of our survival, or, conversely, a source of self-destruction? Can we use the knowledge we gain to prevent global catastrophes, or are we doomed to repeat historical cycles? These questions provoke deep reflections on our place in the world and how we perceive our existence in the context of the entire history of the planet. Some theories suggest that intelligent life can arise and disappear in cycles, which may indicate recurring conditions that either facilitate or hinder evolution. This leads to contemplations on how climate conditions have changed over millions of years and how they have influenced life on Earth. Scientific research shows that over the past 500 million years, the planet has experienced at least 5 major mass extinctions, including the well-known extinction of the dinosaurs, which occurred around 65 million years ago. It is important to consider that each of these catastrophes could have marked the beginning of a new era for life, possibly even for intelligent beings who might have reappeared on the planet. Discussing these questions opens new horizons for understanding not only our history, but also our future and how we can influence it. In this context, an interesting aspect arises. Could there have been other forms of intelligent life besides humans, and how might they have perceived the world? In such reflections, we encounter the concept of the diversity of intelligent life forms, which could lead to new discoveries about the very notion of intelligence and its manifestations in different conditions. The concept of cosmic solitude posits that we may be the only intelligent beings in the universe, and this notion creates a sense of isolation in us. If we were to discover the remnants of ancient non-human civilizations, this could fundamentally alter our perception of ourselves and our role in the cosmos. We might no longer feel alone on this blue planet, but rather realize that other intelligent life forms once existed, perhaps possessing highly advanced technologies and cultures. For instance, if archaeologists found the remains of an extraterrestrial civilization on Mars or the Moon, this would not only challenge our understanding of what it means to be human, but also spark a new wave of scientific research and philosophical contemplation. We would begin to ask questions about why these civilizations disappeared, what their achievements and mistakes were, and how their experiences could help us avoid our own catastrophes. Furthermore, the discovery of such civilizations could lead to global changes in politics, culture, and even religion, prompting people to reevaluate their views on life, the world, and their place in it. For example, if we found the ruins of a great city built by non-humans, this could serve as evidence that intelligence can manifest in various forms and conditions, implying that human history is just one chapter in the infinite book of the universe. Such discoveries could inspire us to seek new ways of communication and interaction, perhaps even to establish contact with other beings if they still exist beyond our planet. The idea that we are not alone could motivate humanity to adopt a more responsible attitude towards our planet and each other, understanding that our existence is not the final destination but a part of a broader process. Meanwhile, we continue to explore and ask questions, with the traces of ancient civilizations remaining mere hypotheses awaiting discovery. The cosmic heritage of humanity is not merely an abstract concept, but a complex set of philosophical questions about our place in the universe and our responsibility towards future generations. It is believed that humanity, as the continuation of a line of intelligent life on Earth, should approach its development consciously, taking into account the achievements of preceding civilizations. For instance, the ancient Sumerians, who left behind the first written records and technologies, already pondered questions about the nature of existence and their place in the world. Their approach to life, which included deep spirituality and respect for nature, can serve as a lesson for us. We, modern people, should remember that our heritage is not just in material achievements, but also in how we understand the world around us and interact with it. There is a view that further technological development should proceed in harmony with the ethical principles laid down by our predecessors. For example, The ancient Egyptians not only built pyramids, but also created complex systems of beliefs that connected them with the cosmos and eternity. This raises the question of what culture we will leave behind. Scientific achievements, such as space exploration, should be accompanied by an awareness of our responsibility towards the planet and the future. We cannot ignore the lessons of history, for every lost civilization has left a warning that thoughtless use of resources can lead to catastrophe. Philosophers like Kant argued that humanity should strive for moral progress, and this is especially relevant in light of today's challenges, such as climate change and social inequality. It is as a civilization, we stand at a crossroads, where we can either continue on a path of destruction or choose a path of conscious existence, taking into account the lessons of the past. This raises the question of how we can take responsibility for our heritage and how we will pass it on. We must remember that each step in development, each decision, each interaction with nature is not just an action, but a reflection of our philosophy and understanding of our place in the cosmos. In this context, the awareness of our responsibility becomes a key factor that will determine who we will become in the future. The question of how we will relate to our planet and to each other requires deep reflection and discussion, for it is from this that our legacy will depend. It is important that this legacy should not be just a collection of technologies, but should be based on principles of respect and harmony. When we begin to consider the possibility of non-human forms of intelligence in the distant past of Earth, we are confronted with a series of metaphysical questions concerning consciousness and reason. What is reason? What are its boundaries? Could there have been civilizations on our planet whose consciousness operated on principles different from human ones? For instance, history often mentions enigmatic beings such as the Atlanteans or Lemurians. Did they possess systems of thought that we cannot comprehend or perceive? One of the key problems is the question of how we define intelligence. If we consider intelligence as the ability to solve problems, adapt to the environment, and interact with it, then perhaps some animals or even ecosystems possess forms of intelligence that we simply do not recognize. For example, some researchers assert that dolphins and elephants exhibit complex forms of social interaction and even cultural traditions. But how does this relate to the concept of reason? Furthermore, if we consider the possibility of extraterrestrial civilizations, a more complex question arises. How could their consciousness function in entirely different conditions, unlike those on Earth? This challenges our ability to perceive and understand such forms of reason. And what about those artifacts that archaeologists sometimes find? Some of them, like the mysterious stones from Oklahoma, spark debates about whether they were created by intelligent beings that are not human. These discoveries only fuel discussions about the possibility that we are not the only intelligent beings on the planet. Some researchers even suggest that in ancient times there may have existed forms of intelligence that used technologies far ahead of our time, but for some reason disappeared. The question of how such forms of intelligence could interact with the world around them remains open. In this context, it is worth mentioning that in different cultures, there are myths and legends about ancient beings who possessed extraordinary abilities and knowledge. For example, in Sumerian texts, there are mentions of the Anunnaki, who supposedly taught humans various arts. These myths may reflect not only cultural representations of the world, but also real encounters with other forms of reason that humanity was unable to interpret adequately. Ultimately, reflecting on the possibility of non-human intelligence in the past, we encounter numerous questions about the nature of reason and consciousness that still await investigation. In this regard, it is important to pay attention to finds that may shed light on these mysteries, such as fossils or artifacts with unusual characteristics. Ethical aspects of searching for and studying traces of ancient civilizations are becoming increasingly relevant in light of new discoveries. For instance, archaeologists often face the challenge of preserving cultural heritage that can be destroyed by incompetent actions or uncontrolled tourist expansion. It is crucial to remember that each discovered artifact is not merely an object, but a part of history that can tell us about the lives and customs of vanished peoples. For example, the discovery of a ceramic vessel can provide insights into culinary traditions, while tools can reveal information about technology and lifestyle. Researchers must consider that many cultures they interact with have their own notions of sacredness and respect for the land they inhabited. In some cases, even the names of sites where excavations are conducted may be sacred to local communities, and their disregard can lead to discontent and protest. It is also important to strike a balance between scientific interest and respect for the rights of the descendants of the civilizations whose traces are being studied. This raises questions about who has the right to make decisions about what to do with discovered artifacts. Should they remain in the country of discovery, or should they be sent to international museums? Ethical dilemmas also concern the way information about ancient cultures is presented to avoid stereotypes and distortions that can arise from oversimplified perceptions. For example, depicting ancient civilizations as savages can overshadow their achievements and contributions to world history. It is, for instance, in some countries, the practice of returning artifacts that were taken in the past is common, which helps restore the connection between a people and its history. As a result, such practices can lead to a deeper understanding and respect for cultural heritage, which is an integral part of human history. Considering all these aspects, it becomes clear that the study of ancient civilizations requires not only a scientific approach, but also an awareness of the responsibility for preserving cultural heritage. Moreover, understanding and respect for vanished cultures can enrich our perception of human history, opening up new horizons. For example, in the 20th century, efforts were made to restore and preserve ancient monuments, such as Mayan temples in Central America, which became possible thanks to close cooperation between scientists and local communities. The concept of cosmic ethics explores moral obligations between intelligent species that may exist in different time periods and on various planets. This idea is based on the assumption that intelligent beings, regardless of time and space, may share similar moral principles rooted in the understanding of the value of life and existence. For instance, if we ever establish contact with other civilizations, questions about how we should treat them and what obligations we may have will become highly relevant. This could involve obligations to protect their cultures and ecosystems, as well as ethical dilemmas related to potential interference in their development. Furthermore, this concept may consider the responsibility of more advanced civilizations towards less advanced ones, where higher technologies and knowledge may raise moral questions about intervention in the natural course of development of other species. Such reflections raise questions about whether we can claim ethical superiority and in what cases it might be justified. For example, if humanity gains the ability to colonize another planet, should we consider the culture and ecosystems of any existing life forms if they are discovered? These questions require deep analysis and may influence our future actions. It is important to note that cosmic ethics not only concerns interaction with other intelligent beings, but also includes responsibility towards future generations of humans. We must consider what legacy we leave for those who will come after us and how our actions may impact their lives. In this, questions related to cosmic ethics become particularly relevant in light of current expeditions to Mars and other celestial bodies, where scientists exploring colonization possibilities must consider not only technological but also ethical aspects of their actions. As a result, the concept of cosmic ethics offers a broad field for discussion and reflection on how humanity should understand its place in the universe and its moral obligations towards intelligent beings that may exist elsewhere. It is important to remember that ethical norms change over time, and what may seem acceptable today may raise many questions and disputes tomorrow. Ultimately, cosmic ethics is an integral part of our understanding of how we should interact with other civilizations if they are ever discovered, and how we should view our own actions in the broader cosmic context. In this regard, even contemporary research and colonization plans open new horizons for discussing moral questions that may arise in the future. The concept of legacy for the future is becoming increasingly relevant in the context of contemporary trends and challenges that humanity faces. Legacy is not just what we leave behind, but also how our actions and decisions today impact the lives of future generations. We are talking about social, cultural, and environmental aspects that shape our collective existence. For instance, a legacy can encompass protecting the environment, preserving cultural traditions, and promoting sustainable development. This requires not only an understanding of historical context, but also active participation in creating living conditions that meet the needs of future generations. It is crucial to realize that every step we take today can form the basis for new realities tomorrow. The effort to preserve nature, maintain cultural diversity, and develop technologies in a conscious manner creates the possibility for a truly sustainable legacy. This concept becomes particularly important in the face of global challenges such as climate change and social inequalities, which demand not only attention but also concrete actions. Ultimately, legacy for the future is not just an abstraction, but a real responsibility that lies on our shoulders. One of the key aspects of this approach is the need to understand that each of our actions, even the smallest, can have long-term consequences. Creating long-term messages for future civilizations that may emerge on Earth after the extinction of humanity is a complex task. Throughout history, there have been examples of preceding intelligent species leaving messages for their descendants. For instance, ancient Egyptians created hieroglyphic inscriptions on the walls of temples and tombs to transmit their knowledge and beliefs to future generations. These are, in a sense, time capsules that were meant to preserve culture and traditions even after the author's deaths. Another example is Stonehenge, which may have been used for astronomical observations and the transmission of knowledge about time and natural cycles. The challenge lies in making such messages understandable after thousands of years, when language and culture may have changed beyond recognition. For example, the Pyramid of Cheops was not just a tomb, but also a symbol meant to convey the idea of the greatness and immortality of the pharaoh to future generations. Scientific experiments show that for long-term information transmission, it is necessary to consider changes in climate and geological processes that could damage or destroy physical data carriers. There are even projects like Solar Messenger that propose the creation of special objects designed to outlast humanity and convey information about our civilization to subsequent intelligent species. In this context, both the form and content of the message are crucial, with the content needing to be universal and understandable. For example, projects to create messages to planet Earth include images, mathematical concepts, and physical laws that could be understood by any intelligent life. Such ideas have already been discussed in scientific circles, where the focus is on ensuring the longevity and comprehensibility of information to avoid misunderstandings. The remaining messages could serve not only as evidence of human existence, but also as a valuable source of knowledge for future civilizations that may face similar challenges. It is important to note that even if messages are left, there is no guarantee that they will be found or understood. Deep-time information repositories represent a concept that could fundamentally transform the way knowledge is transmitted between civilizations separated not only by temporal, but also geological epochs. One example of such repositories is the Global Library Project in Norway, where seeds of plants are stored in permafrost, capable of reviving agriculture in the future. But imagine if we could create structures that not only preserve biological, but also cultural heritage. For instance, using special materials that can withstand extreme conditions, such as high temperatures or radiation, could form the basis for durable archives. Additionally, we could consider the creation of digital repositories based on quantum technologies, which theoretically could preserve information for millions of years without loss. Such repositories could include not only texts and images, but also audio recordings, videos, and virtual replicas of historical objects and sites. This would allow future generations not just to read about the past, but to experience it as if they were witnesses to the events. The deep time repository model also implies the creation of a metadata system that would explain the context and significance of the contained information, which is critically important for understanding the heritage. If such technologies are developed, they could serve not only for storing knowledge, but also for transmitting it between civilizations that may exist in different corners of the planet or even beyond it. Scientists are already contemplating how such repositories might look and what requirements they should meet to ensure that information remains accessible for millions of years. For example, using corrosion-resistant materials like titanium or special composites that are not subject to decay over time could be considered. There is also the idea of creating archives in the Earth's interior, where conditions are more stable and less subject to change. In such places as caves or old mines, data could be stored in conditions that protect it from external influences. Such repositories could become important landmarks on the map of civilizations, preserving not only their achievements, but also the lessons they have learned along the way. The concept of cosmic altruism opens up intriguing possibilities for understanding the interaction between civilizations. This idea suggests that advanced civilizations may deliberately leave their knowledge and technologies for future intelligent beings, even if they are aware that they will never meet them. It is important to note that such actions may be driven not only by the desire to help, but also by an awareness of one's place in the universe. This reminds us of how ancient cultures left their written records and artifacts for future generations, hoping that their knowledge would not be forgotten. For example, the Sumerians, who created cuneiform writing, left us not only records of their lives, but also the foundations for future letters and documents. Cosmic altruism may also be connected to the concept of parallel civilizations, where more advanced societies, possessing technologies that could help less developed ones, choose to leave their achievements as monuments in space, such as signals, or even physical objects that could be discovered. Research shows that such signals could contain information about scientific achievements, culture, and even philosophy, providing future civilizations with the opportunity to learn from others' experiences. This approach can provoke controversy, as many scientists believe that such an initiative would likely be perceived as interference rather than help. Nevertheless, the idea of advanced civilizations leaving their traces in space raises interesting reflections on how we can interact with other forms of life and how we ourselves will perceive the legacy left by our predecessors. In this context, the concept of cosmic altruism remains open to further research and discussion, raising numerous ethical and philosophical questions about our place in the vast cosmos. To date, many theories have been proposed about how this might happen, but none provide a definitive answer to the question of the true nature of such intentions. The question of the existence of ancient prehistoric civilizations remains open and continues to spark debate among scholars and history enthusiasts. There are numerous hypotheses that suggest that humanity could have existed in various forms long before we are accustomed to believing. For instance, research indicates that in different corners of the world, such as Mesopotamia, the Indus Valley, or even in Antarctica, there could have been highly advanced communities that left behind traces that remain unexplained to this day. These civilizations might have possessed knowledge and technologies that we now consider modern, but their achievements remain in the shadows of history. Some archaeologists claim that the oldest known structures, such as Göbekli Tepe in Turkey, dating back tens of thousands of years, could change our understanding of the chronology of human cultural development. They propose looking at our history not as a linear process, but as a complex network of interconnections and influences. This leads us to question our place in time and space. Perhaps we are not the first to master technologies, and this makes us ponder the responsibility we bear for our planet and its future. Every day, as we continue to explore and discover new things, we must remember that the existence of life on Earth requires careful treatment and understanding. We live in an era where our actions can significantly impact the future, and the question of responsibility for preserving intelligence and life on the planet becomes particularly relevant. Reflect on this before you sleep, when darkness envelops the world and opens up boundless possibilities hidden in the depths of time and space. Feeling this sensation, you may find inspiration for your own reflections. Take the time to ponder how amazing and multifaceted our world is, and how much more there is to discover. In a world where each new day brings us new knowledge and discoveries, it is important to remember that our understanding of the past can influence our future. Facts about ancient civilizations, such as the discovery of traces of ancient culture in India in the 20th century, continue to amaze and inspire researchers worldwide.